Hello there and welcome to Science for Sleep, where curiosity gets cozy, the universe slows down just enough to think about it, and science takes the scenic route toward rest. Tonight, we are drifting into a story that sounds almost too dramatic for a quiet night under the stars. It is the story of a galaxy that was eaten by the Milky Way. Not in a sudden bite, of course. Galaxies do not chew, thankfully, and the Milky Way does not sit in the dark with a knife and fork, politely carving up its smaller neighbours. But over billions of years, gravity can do something that looks, from a safe distance, very much like eating. It pulls, it stretches, it tears, it folds one system into another until the smaller galaxy is no longer a separate little island of stars, but a trail of evidence scattered through the larger one. And the strangest part is that this swallowed galaxy is not simply gone. It is still around us. Its stars are still moving through the Milky Way. Some of them are passing through the wide, faint halo that surrounds our galaxy. Some are mixed into the starry history of the place we call home. They do not come with labels attached, of course. There is no tiny tag on a distant star saying, "I used to belong to another galaxy, please return if found." That would make astronomy easier and perhaps a little funnier. Instead, astronomers had to notice the way these stars moved, the way they looped through the galaxy, the way their paths did not quite match the calm circular traffic of the Milky Way's disk. And when enough of those strange motions were measured, a hidden story began to appear. The name given to that ancient visitor is Gaia Sausage, or more fully Gaia Sausage. It is not the most elegant name ever attached to something in the heavens, I'll admit. The universe gives us names like Andromeda, Orion, Cassiopeia, and then suddenly Sausage, but there is a reason for it. The name comes partly from Gaia, the European Space Agency spacecraft that has been measuring the positions and motions of stars with extraordinary precision, and partly from the odd shape that these stars made in certain diagrams when astronomers plotted their movements. They formed a long, stretched-out pattern, rather like a sausage. Science, for all its equations and noble purpose, sometimes looks at a graph and says, well, that looks like lunch. And honestly, we should appreciate that. It keeps the cosmos humble. But behind the slightly amusing name is a serious event. Long ago, when the Milky Way was younger, messier, and still growing into the galaxy we know today, it collided and merged with a smaller galaxy. This was not a tiny snack. It was one of the most important mergers in our galaxy's history. The smaller galaxy was torn apart, its stars thrown onto long looping paths, and the Milky Way itself was changed by the impact. The crash helped build parts of the halo, stirred the early disk, and left behind a stellar fossil record that astronomers are still reading. Imagine finding bones beneath the floorboards of your house, except the house is a spiral galaxy. The bones are stars, and the floorboards are about 100,000 light-years wide. A little inconvenient for an afternoon inspection, but very useful if you have a space telescope and patience. Before we go deeper into that ancient collision, I'd love to ask you something simple. Where are you listening from tonight? Are you somewhere quiet with the room dim and the day finally letting go? Are you under a cloudy sky where the Milky Way is hidden completely, or somewhere dark enough to see a faint white band spread overhead like a soft stain of light? And what time is it where you are right now? It feels fitting to ask that while talking about a galactic event that happened billions of years before any human being ever looked up and wondered what the stars were. Right now, each of us is sitting in a small local moment. A clock on a phone, a lamp beside a bed, a late evening cup of tea perhaps. And above all of it, the Milky Way carries memories so old that our own lives are barely sparks in comparison. If you find this kind of journey soothing, or if you enjoy letting science become a calm companion at the end of the day, I'd be very grateful if you gave the video a like and maybe subscribed. It helps this quiet corner of the internet reach more tired minds, more curious listeners, and perhaps a few people who came for sleep and accidentally learned about galactic cannibalism, which, to be fair, is a fairly unusual bedtime subject. But that is the nice thing about the universe. Even its most violent stories can become strangely peaceful when we tell them slowly enough. So, settle in. Let your shoulders loosen. Let the day move a little farther away. Tonight we are not racing through space. We're taking the long way around, because the long way is usually where the interesting details are hiding. We're going to look at our galaxy not as a perfect spiral floating untouched in the dark, but as a place with a past, a place built from collisions, leftovers, accidents, and ancient encounters. The Milky Way is not just a calm river of stars. It is also a record of things it has absorbed. It is a home made partly from other homes. From Earth, the Milky Way can look gentle. If you have ever seen it away from city lights, it does not look like violence. It looks like a pale river, a soft cloudy band stretched across the night. For thousands of years, people looked at that band and gave it stories. Some saw a road, some saw spilled milk, some saw a path for souls, animals, spirits, gods, heroes, or wanderers. It was beautiful long before anyone knew what it was, and then, with telescopes, measurements, and a great deal of careful thinking, we learned that the band is not a cloud at all. It is the combined light of countless stars seen from inside the disk of our own galaxy. We're not looking at the Milky Way from outside, the way we see pictures of other spiral galaxies. We're inside it, like a fish trying to understand the shape of the ocean while swimming somewhere near the middle. That makes the Milky Way surprisingly hard to study. You might think our own galaxy would be the easiest galaxy to understand because we live in it. But living inside something can be inconvenient. If you're standing in a forest, it can be hard to see the shape of the whole forest. You see trunks, branches, leaves, paths, shadows. You can walk through it, smell it, hear it, and still not know what it looks like from above. The Milky Way is a little like that. We see stars in every direction, but dust blocks some views. Distances are difficult, motions are subtle, and the galaxy is not holding still for a portrait. Everything is moving. The sun orbits the center. The stars around us drift and swing. Clouds of gas rotate. Dwarf galaxies pass nearby. The whole system is alive with motion, though on timescales so long that it seems still to us. For most of human history, we could admire the Milky Way, but we could not read its past very clearly. We did not know which stars were born here, and which stars might have arrived from somewhere else. We did not know how many small galaxies had been pulled apart and mixed into our own. We did not know that the night sky above us was, in a very real sense, full of fossils. Not fossils made of bone or shell, but fossils made of motion. Because stars remember where they came from, not with thoughts, of course, but with their orbits, their chemistry, their ages, and their paths through the galaxy. A star that formed in the Milky Way's disk usually shares the general rotation of that disk. It moves around the galactic center in a relatively organized way, like a car following traffic around a huge roundabout. Not perfectly, because the galaxy is not a tidy clockwork toy, but generally with the crowd. A star that came from another galaxy may move differently. It may dive inward and outward. It may travel on a stretched path. It may pass through the halo instead of staying close to the disk. It may carry chemical clues from the smaller galaxy where it formed, because galaxies enrich their stars in different ways depending on their histories. If you can measure enough of these details, you can begin to separate the local citizens from the ancient immigrants. You can begin to see that the Milky Way is not one simple population, but a mixture. This is where Gaia changed the story. Gaia is not a telescope in the ordinary sense, not a telescope built mainly to take pretty pictures for us to admire, although we certainly appreciate those when we get them. Gaia's great task has been measurement. It has been mapping the positions, distances, and motions of huge numbers of stars with a level of accuracy that would have sounded almost unreasonable to earlier astronomers. It is like taking a census of the galaxy, but instead of asking people for their address and occupation, you ask stars where they are, how far away they are, how fast they are moving, and which direction they're going. A normal census might tell you who lives in a city, Gaia's census tells us how the city itself is moving, and which residents may have come from a city that no longer exists. The spacecraft was launched to create a three-dimensional map of the Milky Way, and over time, its data gave astronomers something astonishing. In the stellar halo around our galaxy, there were stars that did not move like the more familiar disk stars. They were on highly elongated orbits, plunging in and out toward the galactic centre, rather than smoothly circling around it. Their motion looked like debris from a major collision, not just a few stars here and there, not just a small stream from a tiny companion, but a large population that seemed to point back to one dramatic ancient event. Think of stirring cream into coffee. First you can see distinct swirls, bright ribbons folding through dark liquid. Wait long enough and the cream mixes in. The pattern softens, the boundary disappears. But if you had a magical way to track each tiny droplet, you could still reconstruct the motion. You could say, this part came from that first pour, this swirl was stretched by that turn of the spoon, this pale streak is the ghost of an earlier shape. The Gaia Sausage is somewhat like that, except the coffee is the Milky Way, the cream is a smaller galaxy, and the spoon is gravity, which has been stirring for billions of years with no concern at all for kitchen cleanliness. The swallowed galaxy did not vanish in one instant. Galactic mergers take time. When two galaxies meet, the spaces between their stars are so vast that the stars themselves rarely collide. That is one of those facts that sounds wrong at first. A galaxy collision sounds like fireworks, crashes, sparks, and stars slamming together in every direction. But galaxies are mostly empty space. The real action comes from gravity. Each galaxy pulls on the other. Their shapes distort. Stars are dragged onto new paths. Gas clouds may be squeezed, heated, or pushed into making new stars. Dark matter halos overlap and merge. The smaller galaxy loses its structure. With every pass, more of it is peeled away, until what once had a centre, a shape, and a separate identity becomes a scattered population within the larger galaxy. And because this happened so long ago, we do not see the Gaia Sausage as a neat little galaxy beside us. There is no small spiral or dwarf galaxy still visibly intact with a sign saying, "Former victim of the Milky Way." What remains is more subtle. It is in the halo, it is in the motions, it is in globular clusters and stars whose paths still carry the memory of that ancient fall. The galaxy was eaten, but not erased. That distinction matters. In astronomy, destruction does not always mean disappearance. Sometimes it means transformation. A smaller galaxy can lose its name, its shape, its independence, and still remain present in the larger body that absorbed it. There is something quietly strange about that. When we look up at the night sky, we usually think of the Milky Way as our galaxy, our familiar star city, the place where the sun was born and where Earth has spent its entire history. And that is true. But it is not the whole truth. The Milky Way is also made of things that were once not Milky Way at all. It has grown by collecting gas, forming stars and merging with smaller systems. It is not a single untouched object. It is a long record of appetite and accident. A galaxy is not just born and then left alone. It is shaped by what it meets. The phrase, "the Milky Way ate a galaxy," sounds dramatic, almost mischievous, but it points toward one of the most important ideas in modern astronomy. Large galaxies grow partly by absorbing smaller ones. This process is called hierarchical formation. Small structures form first, then merge into larger structures over cosmic time. Dwarf galaxies become ingredients in bigger galaxies. Star clusters are pulled apart. Streams of stars wrap around galactic halos. The universe builds upward, but not politely. More like a child making a model out of many other models, keeping some pieces, breaking others, and somehow ending up with something impressive on the table. Our Milky Way is still doing this today, though not always with the same intensity. The Sagittarius dwarf spheroidal galaxy, for example, is currently being torn apart by the Milky Way, leaving streams of stars around us. The Magellanic Clouds, those two neighbouring dwarf galaxies visible from the southern hemisphere, are also involved in a long gravitational relationship with our galaxy. The Milky Way may look settled, but it is not finished. It is still growing. It still has companions. It still has a future collision waiting far ahead with Andromeda, although that is so far in the future that your calendar does not need a reminder. The Gaia Sausage matters because it tells us about a much earlier, much more formative event. It happened when the Milky Way was still young enough to be changed deeply by a major impact. The collision may have helped puff up the early disk into what astronomers call the thick disk. It contributed stars to the inner halo. It may have changed the shape and structure of the galaxy in ways that are still being studied. It is not just a little footnote in our galactic history. It is more like discovering that the house you live in was built after an enormous storm, and many of the walls still contain timber from an older building that collapsed nearby. One of the comforting things about astronomy, if we can call it comforting, is that it makes even enormous events feel calm because of the timescales involved. A galaxy merger is violent in a gravitational sense, but it unfolds over hundreds of millions or billions of years. If you could somehow watch it sped up, it would look like a dramatic collision, a great distortion of star clouds and dark matter. But if you live through it from the point of view of a single star, the changes might be slow beyond imagination. The sky would shift over ages, orbits would change, the galaxy would thicken and stir. But there would be no sudden wall of stars rushing past like traffic. Space is too large for that. Even cosmic violence has a very patient side. That patience is part of what makes the Gaia Sausage such a good story for a sleepy journey. It is huge, but not frantic. It is dramatic, but ancient. It tells us that the calm band of the Milky Way is carrying the remains of an old encounter, and that the stars overhead are not just lights, but clues. Some of them are native to this galaxy. Some may be descendants of old disrupted systems. Some have crossed the Milky Way on strange paths for billions of years, moving through the halo like sparks from a fire that burned out before Earth existed. And we're here very late in the story, listening from one small planet around one ordinary star, trying to understand an event that happened long before the sun was born. That is one of the lovely oddities of science. We arrive after the fact and still manage to investigate. We did not see the collision. We did not watch the smaller galaxy fall in. We were not here when its stars were scattered across the Milky Way. Yet the evidence remained patient. The stars kept moving. Their orbits kept their clues. Their chemistry kept its record. And eventually, after billions of years, a spacecraft named Gaia measured enough of them for us to notice the pattern. When you look up at the Milky Way on a clear dark night, it does not immediately look like a place with a violent past. It looks calm, it looks soft, it looks like someone brushed a pale stripe across the sky and then left it there for anyone patient enough to notice. If you are somewhere far from city lights, away from street lamps and glowing windows and the small, stubborn brightness of phone screens, that band can seem almost still. It crosses overhead in silence. It does not rumble. It does not flash. It does not announce that it has spent billions of years pulling smaller galaxies apart and folding their stars into its own body. The Milky Way, from where we stand, looks peaceful in the way an old library looks peaceful. Quiet shelves, dim corners, dust in the light, and no obvious sign that half the books were taken from other libraries long ago. But that is the trick of living inside a galaxy. We see the present surface of it, or at least the part of the surface available to our eyes. We see stars spread across the night, and our minds naturally turn them into something gentle, a background, a familiar ceiling, a calm arrangement of lights above the ordinary business of life. People walk dogs beneath it, drive home from work beneath it, make wishes beneath it, and occasionally look up for 3 seconds before walking into a garden chair. The sky feels like scenery. Yet in astronomy, scenery is rarely just scenery. It is evidence. The quiet band above us is not a finished painting. It is a moving system full of old collisions, stretched streams, heated stars, missing neighbours, and the remains of things that once had names of their own. The Milky Way is a spiral galaxy, and that word spiral can make it sound neat and graceful, like a seashell or a swirl of cream in coffee. From far away, if we could leave our own galaxy and look back from intergalactic space, we would see a wide, flattened disk with arms winding around a bright central region. We would see gas and dust and star-forming regions. We would see the glow of billions of stars blended together into structure. It might look elegant, and in a way it is, but elegance is not the same thing as peace. A spiral galaxy is not a decorative object. It is a gravitational machine, a vast turning system in which stars orbit, gas clouds collide, supernovae explode, black holes feed, and smaller galaxies pass too close for their own comfort. It is beautiful, yes, but it is the kind of beauty that comes from motion, pressure, and time. Our Sun is only one star in this system, located in the disk of the Milky Way, far from the crowded centre and far from the outer edge. We move around the galactic centre at tremendous speed, though we do not feel it because everything around us is moving along with us. This is one of those facts that should make us feel dizzy, but usually does not. You can sit perfectly still in a chair, perhaps under a blanket, perhaps half asleep, and still be travelling around the centre of the galaxy with Earth, the Sun, and all the planets. You're not doing anything wrong. That is simply the normal commute of a star system. No ticket required, no platform announcements, and thankfully no replacement bus service. The disk around us is only part of the Milky Way. There is also a central bulge, a crowded region of older stars near the middle. There is a bar, a stretched structure crossing the centre. There are spiral arms rich with gas, dust, and young bright stars. Around the disk is a much larger, much fainter halo, a huge region containing old stars, globular clusters, dark matter, and the remains of past mergers. The halo is not bright to the eye. You cannot simply look up and see it as a shining shell. But it is there, surrounding the visible disk like a dim memory around a brighter thought. And that halo is one of the places where the Milky Way's less peaceful history is written most clearly. A calm galaxy would have stars moving in tidy patterns, with every population where you expect it, every orbit sensible, every structure explained by simple rotation. The Milky Way does not do that. Many stars in the disk do move in a broadly organised way, circling the galactic centre in the same general direction, like leaves carried around in a slow whirlpool. But beyond that familiar order, astronomers find stars moving on stranger paths. Some dive inward and outward rather than calmly circling. Some travel high above or below the disk. Some move against the general rotation. Some gather into streams, long trails of stars pulled from smaller systems. Others sit in globular clusters whose ages, motions, and chemistry hint at origins outside the Milky Way itself. It is as though the galaxy has drawers full of objects that do not belong to the original furniture set. This matters because stars are not only lights, they are records. A star's motion can tell us about the gravitational events it has experienced. Its chemical makeup can tell us about the environment where it formed. Stars born in small dwarf galaxies often have different chemical patterns from stars born in larger galaxies, because smaller galaxies make and recycle elements differently. They have different rates of star formation, different histories of supernova explosions, different ways of enriching their gas. So when astronomers study stars carefully, they are not just asking, where are you now? They are asking, where were you made? What kind of galaxy raised you? And why are you moving through the Milky Way as if you remember a different home? That idea, that stars can carry old addresses in their chemistry and motion, is one of the great tools of galactic archaeology. It is a lovely phrase, galactic archaeology, because it suggests astronomers brushing dust from ancient ruins. But instead of ruins made of stone, the ruins are moving points of light. Instead of digging into soil, astronomers dig into data. They measure positions, velocities, brightness, colours, spectra, ages, and elemental abundances. They look for patterns that should not be there if the Milky Way had grown calmly by itself. And again, those patterns say the same thing. The Milky Way has not been alone. It has had visitors. Some passed by, some survived, some were pulled apart, some became part of us. One of the reasons the Milky Way can appear peaceful is that galactic violence happens slowly. When we say the Milky Way ate a galaxy, we're using a dramatic human word for a process that unfolds over enormous spans of time. No one saw a single moment when a smaller galaxy crossed a line and vanished. There was no cosmic dinner bell. A dwarf galaxy falling into the Milky Way would have orbited, plunged, lost stars, been stretched by tides, and gradually dissolved over many passages. To a human observer, each stage would seem almost frozen. A star might spend millions of years moving along one part of its path. A stream might take hundreds of millions of years to wrap around the halo. A merger can be one of the most important events in a galaxy's history, and still be far too slow to look dramatic in any single lifetime. This slow pace can fool us. We're used to violence being fast, a crash, a break, a flash, a falling glass, a door slamming in the wind. But gravity is patient. Gravity does not need speed to be powerful. It has all the time in the universe, or at least a very large portion of it, which is more than most of us can say on a Monday morning. Gravity can take a small galaxy and pull at the near side more strongly than the far side. That difference is called a tidal force. Over time, those tidal forces stretch the galaxy. Stars loosen from their original orbits. The smaller system begins to unravel. It becomes a stream, a cloud, a set of strange orbits, a smear in phase space, which is the kind of phrase astronomers use when they are being very precise and not trying to sound like they are describing a haunted weather forecast. The Milky Way's halo contains many signs of this kind of tearing and gathering. One of the clearest examples still being disrupted today is the Sagittarius dwarf spheroidal galaxy, a small galaxy being pulled apart by the Milky Way's gravity. Its stars form streams that wrap around our galaxy. That is happening now in cosmic terms. It shows us that the Milky Way is not only a relic of old mergers, but an active participant in ongoing ones. It is still shaping its surroundings. It is still interacting with smaller companions. The large and small Magellanic clouds, visible from the southern hemisphere, are also caught in a gravitational relationship with the Milky Way, and their future is tied to ours. So when we talk about the Milky Way as a galaxy with a violent past, we should not imagine that the past is completely over. The galaxy is calmer now than it may once have been, but it is not retired. Still, the great event connected to the Gaia Sausage was not just any small disturbance. It was a major merger from the Milky Way's early life, a time when our galaxy was still assembling its structure. The smaller galaxy that fell in was large enough to leave a deep mark. It contributed many stars to the halo, and its impact may have helped heat and thicken the young disk. Heating, in this context, does not mean the stars were warmed like soup on a stove. It means their orbits became more energetic and less orderly. A thin, cold disk of stars has stars moving in more circular, organised paths. A heated disk has stars tossed onto more varied orbits, moving higher above and below the plane. The language is a little odd at first, but useful. Galaxies can be dynamically hot or cold, which sounds like they should come with a thermostat, but really describes how stirred up their motions are. When the Milky Way was younger, a substantial collision would have disturbed it, not destroyed it, but changed it. Think of a pond with a smooth surface. Drop a stone into it, and the pond remains a pond, but ripples spread, mud lifts, reflections distort. Now imagine the pond is made of stars, gas, and dark matter, and the stone is another galaxy. Also imagine the pond is about 100,000 light-years across. This is why astronomers do not get invited to design simple garden features. The point is that a merger can leave long-lasting effects. It can scatter stars. It can compress gas. It can trigger bursts of star formation. It can alter the shape of the disk. It can build up the halo. The visible galaxy we know today carries the consequences of events that happened before Earth existed. The peaceful image of the Milky Way also hides the fact that galaxies grow by consuming smaller systems. This is not unusual behaviour. It is part of how the universe builds structure. In the early universe, matter gathered into small clumps first. Over time, under gravity, those clumps merged into larger clumps. Small galaxies formed, merged, and fed larger galaxies. Larger galaxies gathered more gas and more stars. Galaxy clusters formed from groups. Filaments formed the great cosmic web. Growth in the universe is often a matter of combination. The Milky Way is not guilty of a special crime. It is doing what galaxies do. If anything, it is a fairly ordinary member of a universe where gravity is always trying to bring things together, even as cosmic expansion pulls the largest distances apart. This does not make the story less interesting. Ordinary, on the scale of galaxies, can still be astonishing. It means our own galaxy is not a sealed container. It is a mixture assembled over time from material born in different places. Some of the atoms in our bodies formed in stars that lived and died in the Milky Way. Some may have been part of gas enriched by earlier generations of stars long before the Sun formed. The galaxy around us is full of recycling on a scale that makes a household bin look rather modest. Stars form from gas. Stars make heavier elements. Stars die and return material to space. Galaxies merge and mix their contents. New stars form from old ingredients. Somewhere in that long chain, the material that became Earth joined the story. The Gaia Sausage adds another layer to that story because it tells us the Milky Way's identity is partly inherited from a galaxy it absorbed. We often think of identity as something fixed. The Milky Way is the Milky Way. Andromeda is Andromeda. A dwarf galaxy is a dwarf galaxy. But over cosmic time, these names are temporary conveniences. A small galaxy can become a halo population. A globular cluster can become a clue. A stellar stream can be the last visible handwriting of a system that no longer exists. The Milky Way is not one uninterrupted thing. It is more like a family tree whose branches have grown together so tightly that some old names are hidden in the bark. This is one reason astronomers are so interested in the motions of stars. A photograph of the Milky Way can show where stars are, but motion shows what they're doing. A star's position is a single word. Its orbit is a sentence. With enough orbits, you can begin to read a history. Before precise stellar surveys, many of these histories were blurred. Astronomers knew the Milky Way had a halo. They knew globular clusters were old. They knew dwarf galaxies could be disrupted. But the fine details were hard to separate. There were too many stars, too many distances, too many faint motions across the sky. It is one thing to look at a crowd and notice that people are standing in different places. It is another thing to track how each person is walking, where they came from, and whether a large group entered through the same side door several hours ago. That is why the quiet appearance of the Milky Way changed so much when better data arrived. Once astronomers could measure stellar motions with enough precision, the galaxy began to look less like a smooth population and more like a layered memory. The halo, especially, became a place where past mergers could be found. Some stars had orbits that were very elongated, plunging toward the centre and back out again. These are the kinds of paths expected if they came from a smaller galaxy that fell into the Milky Way on a radial orbit, meaning it moved more like something diving in and out than something smoothly circling around. When plotted in certain ways, those motions formed the long pattern that helped inspire the sausage part of the name. Again, not the most majestic image in astronomy, but very memorable. There are worse fates for a dead galaxy than becoming unforgettable. A less peaceful Milky Way also changes how we think about home. Home usually feels stable. We imagine the galaxy as the address of the sun, the broad cosmic neighbourhood in which Earth has always lived. And it is. But that neighbourhood has been built through change. Its roads were not always in the same place. Its outskirts contain debris from older structures. Its calm present is the result of a restless past. The Milky Way did not begin as a finished spiral and simply remain that way, politely rotating while life eventually appeared on one small planet. It formed, grew, merged, stirred, settled, and continued changing. We live in a galaxy that has survived its own youth. There is also a useful lesson here about appearances. Many things in space look still because they are far away, and because we live too briefly to watch them change. The moon rises, planets wander, comets appear and fade. Those emotions we can notice, but galaxies move on longer clocks. Their arms rotate over hundreds of millions of years. Their mergers unfold over ages. Their stellar streams wrap slowly through halos. The Milky Way looks peaceful because our lives are short and our eyes are simple. The galaxy itself is in motion everywhere. Even the stars that seem fixed in constellations are drifting through space. Given enough time, Orion will change shape. The familiar patterns will loosen. The sky is not a ceiling. It is a snapshot. That snapshot includes the remains of the Gaia Sausage. But recognizing those remains required people to stop thinking of the Milky Way as only a beautiful band and start thinking of it as a set of measurable motions. This story is not written in a single bright object. It is not like seeing a nearby planet or a comet with a tail. It is written in statistics, in the shared behaviour of many stars, in the difference between stars that orbit with the disk and stars that plunge through the halo. This is a quieter kind of discovery, and maybe that makes it even more impressive. No one pointed a telescope at one glowing object and said, "There it is, the swallowed galaxy." Instead, astronomers gathered data from many stars and noticed that a large group seemed to be moving as if they belonged to the same ancient event. So the Milky Way is not peaceful in the simple sense. It is stable enough for stars and planets and life to exist, but it is not untouched. It is not pure. It is not a quiet island that grew alone in the dark. It is a survivor of mergers, a collector of streams, a galaxy with a halo full of old debris and a disk shaped by forces that began long before the sun formed. Its calm appearance is real in one way, because right now, from Earth, the night sky can soothe us. But underneath that calm is movement, memory, and gravity's long history of taking things apart and building something larger from the pieces. If the Milky Way's past is not written in an obvious scar across the sky, then we need another way to read it. We need to look not just at where stars shine, but how they travel. The clue was not a glowing wreckage cloud, or a small galaxy still hanging nearby with ragged edges, waiting politely to be identified. It was not something you could point to in the night sky and say, "There it is, the swallowed one." The remains of the Gaia Sausage were hidden in a much quieter place. They were hidden in motion. Not in the brightness of stars alone, not in their colour alone, not even in where they happened to be sitting in the sky, but in how they were moving through the Milky Way. And that is a very different kind of detective work. It is one thing to look at a star and admire it. It is another thing entirely to ask where it is going, how fast it's travelling, whether it belongs to the crowd around it, and whether its path makes sense for a star that was born here. Astronomers had suspected for a long time that the Milky Way had grown by absorbing smaller galaxies. This was not a wild guess. Other galaxies show tidal streams and disturbed shapes. The Milky Way has satellite galaxies, globular clusters, and faint stellar trails that already hinted at a history of capture and disruption. But suspicion is not the same as seeing the pattern clearly. The problem was that the Milky Way is enormous, crowded, dusty, and inconveniently wrapped around us in every direction. We're not looking at it from outside, where a stream or merger remnant might appear as a faint loop around the disk. We're embedded inside the thing we're trying to understand. which is rather like trying to study the full shape of a storm while standing in one raindrop. For many years, astronomers could measure stars fairly well in one or two ways. They could measure where a star appeared on the sky. They could measure its brightness. For some stars, they could estimate distances. For others, they could measure chemical fingerprints by splitting starlight into spectra. But to find a dead galaxy hidden inside the Milky Way, they needed something more complete. They needed to know how stars were moving in 3 dimensions. A star can move sideways across the sky, which astronomers call proper motion. It can also move toward us or away from us, which is measured through radial velocity, using the tiny shift in its light. And to turn those motions into a real path through the galaxy, you also need distance, because a tiny apparent shift can mean very different speeds depending on how far away the star is. A nearby cyclist and a distant airplane can both seem to move slowly across your view, but one is having a much more dramatic day. This is where Gaia enters the story. Gaia was built for precision, not glamour. It was not sent into space to take the kind of colourful portraits that end up on bedroom walls, although those are lovely and have done a great deal for science posters everywhere. Gaia's work is astrometry, the careful measurement of star positions and motions. It watches stars again and again as it orbits the Sun, measuring tiny changes in their apparent positions. From those changes, astronomers can calculate parallax, the small shift that reveals distance, and proper motion, the slow drift of a star across the sky. For many stars, especially brighter ones, Gaia also provides radial velocities. Combined with other spectroscopic surveys, this creates something deeply powerful, a moving map of the galaxy. A normal map tells you where things are. A Gaia-style map tells you where things are and how they are flowing. Imagine opening a city map and seeing not only the streets and buildings, but every person, car, bicycle, pigeon, delivery van, and suspiciously fast dog moving in real time. You could see the main traffic. You could see people walking with the crowd. You could also notice a large group of travellers moving in a strange pattern, all coming from the same direction, crossing the city in a way that does not match the usual commute. That odd group might be the clue that an old parade, a protest, a football match, or a very determined sausage festival had passed through earlier. In the Milky Way, the strange travellers were stars. When Gaia's second major data release arrived, astronomers suddenly had access to precise measurements for an enormous number of stars. It was not just more data, it was a different quality of vision. The galaxy began to look less like a flat picture and more like a moving crowd. Researchers could take stars near the Sun, especially stars belonging to the halo, and plot their velocities in detail. The halo is important here because it is where many accreted stars are expected to live. Disk stars usually move around the galactic centre in a broadly organised rotation. Halo stars, especially those from disrupted galaxies, can have more eccentric, tilted or plunging orbits. They do not always follow the disk's calm circular traffic. They may dive through it, swing far outward and come back again, like visitors who never learn the local road rules. The stars linked to the Gaia Sausage stood out because many of them were moving on highly radial orbits. That means their paths were stretched inward and outward, toward and away from the galactic centre, rather than smoothly around it. Picture a carousel with most horses going around in circles. Now imagine a group of horses somehow charging in and out across the carousel instead, which would be unsafe, confusing, and probably frowned upon by the operator. In the Milky Way, this kind of movement is not a safety violation. It is evidence. Stars on strongly radial orbits suggest a galaxy that fell into the Milky Way on a path aimed deeply inward rather than gently joining the rotation. When astronomers plotted the velocities of these halo stars, the pattern looked unusual. In one kind of velocity diagram, the stars formed an elongated shape, stretched out in a way that reminded researchers of a sausage. And yes, that is where the name comes from, not from the galaxy looking like a sausage in the sky, because it does not. Not from stars arranged in a sausage-shaped constellation, which would be entertaining but sadly not the case. The sausage was in velocity space. That phrase sounds a little like a place where breakfast foods go to become theoretical, but it simply means a diagram where the axes represent motion instead of physical position. The stars were not making a sausage-shaped object you could photograph. Their velocities made a long, fat, distinctive pattern in the data. This is one of those moments where modern astronomy feels almost like translation. The universe gives us something strange, not in ordinary language, but in measurement. A star moves across the sky by a tiny amount. Its light shifts slightly because it is moving toward or away from us. Its distance is inferred from a minute parallax. Then all of that is converted into a velocity through the Milky Way. Multiply this by thousands and thousands of stars and a message appears. Not a sentence exactly, but a pattern. The message says these stars are not random. They share a past. The Gaia Sausage stars were also different from the familiar disk population. Disk stars tend to share the Milky Way's rotation. They orbit in the same broad direction, with relatively small departures compared with halo stars. The sausage stars had less organised rotation and much more plunging motion. Many of them moved as though they had been thrown into the Milky Way's halo by a major collision. They were not simply a few odd stars making a statistical nuisance of themselves, like cosmic troublemakers in the back row. They formed a large population. That matters because small numbers can mislead you. A handful of strange stars could come from many causes. A large coherent group with similar orbital behaviour points toward a shared origin. Astronomers did not rely only on motion either. Motion was the doorway, but chemistry helped confirm the story. Stars carry chemical clues from the gas clouds where they formed. The amount of iron, magnesium, silicon, calcium, and other elements in a star can reveal the enrichment history of its birthplace. A small dwarf galaxy does not usually enrich its gas in the same way as a large galaxy like the Milky Way. It has a different pace of star formation and a different sequence of supernova contributions. So when stars with unusual motions also show chemical patterns distinct from stars born in the Milky Way, the case becomes stronger. It is like finding a group of people walking through a city in an unusual formation, and then discovering they all carry passports from a country that no longer exists. This combination of motion and chemistry is one of the reasons the discovery felt so convincing. The Gaia data showed that many halo stars were moving in a shared, strange way. Spectroscopic information showed that they were not chemically identical to native Milky Way stars. Their ages also pointed to an ancient origin. Put together, the evidence suggested that a large dwarf galaxy had merged with the early Milky Way billions of years ago, leaving behind debris that now dominates much of the interstellar halo. Different research groups described related parts of this same event with slightly different names. One group emphasized the sausage-shaped velocity pattern. Another identified the accreted galaxy as Gaia Enceladus. Over time, the combined name Gaia Enceladus Sausage became common, which sounds like a mythological creature that got lost on its way to a picnic, but it captures the history of the discovery. The name Enceladus is also meaningful. In Greek mythology, Enceladus was a giant, one of the children of Gaia. That fit the astronomical picture neatly enough, because the galaxy was found through Gaia data, and because the object was large compared with many other systems that merged into the Milky Way. It was not the largest galaxy imaginable, but for a Milky Way satellite long ago it was substantial. It had enough mass, enough stars, and enough gravitational influence to shake the early Milky Way. The sausage part is less mythological and more graphical, but both parts point to the same buried event. Gaia revealed the giant. The velocity diagram gave it a shape. Finding this structure required astronomers to separate halo stars from the much larger population of disk stars. That is not as simple as it sounds. The sky is full of overlapping populations. Stars from the thin disk, thick disk, bulge, halo, and various streams can appear in the same broad direction from Earth. A star does not come with a membership card. Astronomers have to infer its population from its motion, chemical makeup, location, and sometimes age. Disk stars generally rotate with the disk. Halo stars tend to have more random, inclined, or eccentric orbits, but the boundaries are not perfectly clean. The Milky Way is not organized like a filing cabinet, even though astronomers might sleep better if it were. To make sense of this, researchers often use coordinate systems centered on the galaxy rather than Earth. From our point of view, stars move across the sky in complicated ways. But when you convert their positions and motions into a galactic frame, you can ask more useful questions. How fast is this star moving toward or away from the galactic center? How fast is it moving around the center? How much is it moving up or down relative to the disk? These components of motion can reveal whether a star belongs to the disk's rotation or to a more eccentric halo population. The Gaia Sausage stars showed strong radial motion, which means they were moving in and out through the galaxy rather than carrying much angular momentum around it. Angular momentum is a useful idea here, though we can keep it gentle. A spinning figure skater has angular momentum. A planet orbiting the Sun has angular momentum. A disk star circling the Milky Way has angular momentum around the galactic center. Stars born in the disk tend to share that rotating motion because they formed from gas already orbiting in the disk. But stars from an infalling dwarf galaxy can arrive with very different angular momentum. If the dwarf came in on a nearly head-on path, its stars may end up on plunging, elongated orbits after the galaxy is torn apart. That is what the Gaia Sausage pattern suggested. The ancient galaxy did not politely settle into the Milky Way's spin. It came in hard, on a path that sent its stars diving through the inner galaxy again and again. The phrase head-on collision can make the event sound like two solid objects smashing. It was not quite like that. Galaxies are diffuse, with huge distances between stars, so individual star-star collisions would have been extremely rare. But gravitationally it was a major impact. The dark matter halos would have interacted through gravity. Stars would have been pulled onto new paths. Gas, if present, could have been disturbed. The early Milky Way's disk would have been shaken and heated. The smaller galaxy would have lost its structure. Over time, the debris spread out, but the orbital signature remained. That is the remarkable thing. Even after billions of years of mixing, enough information survived for Gaia to reveal the pattern. You might wonder how any motion could survive that long without being completely scrambled. After all, the stars have been orbiting the Milky Way for ages. Shouldn't their paths have mixed until the old galaxy became completely impossible to identify? In one sense, yes, much of the original structure has been blurred. The Gaia Sausage is not a neat stream like some younger disruptions. It is more mixed, more spread out, more deeply folded into the Milky Way. But motion in a gravitational system preserves certain clues. Stars from the same event may still occupy related regions of energy and angular momentum. Their orbits may still share eccentricity. Their chemistry may still mark them as a group. The original galaxy's shape is gone, but the pattern of its debris remains in a deeper kind of space, the space of motions and orbits. This is why Gaia's discovery feels so different from simply seeing a nearby dwarf galaxy. It is archaeology after the ruins have been scattered. It is not finding a fallen wall. It is finding stones built into many later walls and realizing they all came from the same vanished building. The stars are now part of the Milky Way, but their movements betray their origin. They are citizens of our galaxy now, if we can use such a word for stars, but they were not born into the same structure. Their paths still lean backward toward a time when the Milky Way met another galaxy and changed. There is also a nice humility in the method. The Gaia Sausage was not discovered because it was spectacular to the eye. It was discovered because astronomers became good at measuring small things carefully. Tiny shifts, tiny angles, subtle velocities, star after star after star. The story of a galaxy-scale collision was hidden in motions too small for human senses to notice. A star's proper motion across the sky can be so slight, that from year to year, it looks fixed. The ancients called stars fixed stars for a reason. Compared with planets, they seemed motionless. Yet with enough time and precision, that stillness breaks. The fixed stars are not fixed. They are travelling, and their travel has memory. The European Space Agency's Gaia spacecraft made this possible by repeatedly scanning the sky, building a precise catalogue of stellar positions, parallaxes and motions. It did not need to know in advance where the swallowed galaxy was. It simply measured the stars. That is often how big discoveries happen. A survey gathers data broadly and carefully, and then patterns emerge that were not visible before. Gaia did not point at the Gaia Sausage as a single target. It revealed the moving structure of the galaxy, and within that structure astronomers recognized the remains of a merger. Sometimes science is not a flashlight shining on one hidden object. Sometimes it is turning on the lights in an entire room and noticing that the furniture has been arranged by a very old accident. The discovery also showed why the Milky Way's halo is not just a loose scattering of old stars. It is a record of assembly. For a long time, the halo may have seemed like a faint outer population, interesting but not central to the galaxy's identity. Gaia helped show that the inner halo contains a major contribution from this ancient accreted galaxy. In other words, the halo is not merely decoration around the disk, it is a fossil field. The stars out there are part of the Milky Way's growth history. Some were born here, some arrived by merger, some trace events that happened when the galaxy was still young. To study them is to study how the Milky Way became itself. Once researchers recognized the Gaia Sausage, they could begin connecting it to other evidence. Some globular clusters seemed likely to have come in with the same merger. These clusters are dense old groups of stars, and their orbits and ages can help trace past accretion events. Certain halo stars, certain chemical patterns, and certain orbital families began to fit into a larger story. The swallowed galaxy was not just a set of individual stars. It may have brought clusters with it. It may have helped build the halo. It may have disturbed the early disk. It was not a small ripple. It was one of the defining impacts in the early history of the Milky Way. Still, astronomers have continued refining the details. Science rarely stops at one announcement, brushes off its hands and says, "Lovely, we're finished." The mass of the original galaxy, the exact timing of the merger, the amount of gas involved, the connection to the thick disk, the relation between Gaia, Enceladus and other named structures, all of these are active areas of study. Different surveys and simulations help test the picture. Some details shift as more data arrives. That is normal. The central idea remains powerful. A large ancient merger left a distinct population of stars in the Milky Way, and Gaia allowed astronomers to identify it through their motions. And perhaps this is the most interesting part for us, listening quietly on a small planet in the disk. The Gaia Sausage was not found at the edge of imagination. It was found in the data of nearby stars, in the way parts of our own galaxy move around us. The evidence is not only far away in a remote corner of space, it is spread across the sky, passing through the Milky Way's halo, present in the same broad galactic home that contains the Sun. We are surrounded by old motion. The stars overhead are not just arranged in space, they are travelling through history. Some of them carry the memory of a galaxy that came apart before Earth formed, before the Sun formed, before any creature could look up and give the Milky Way a name. That changes the feeling of the night sky a little. It means that the darkness above us is not just deep, but layered. A star may look like a simple point, but its path may be part of an ancient collision. A cluster may look like a glittering knot, but it may once have belonged to another galactic system. The halo may look invisible to the naked eye, but it contains the torn pages of the Milky Way's old biography. Gaia did not create that story. It gave us the measurements needed to read it. So when we say astronomers found the Gaia Sausage hidden in stellar motion, we mean they found a dead galaxy by watching how its stars still move. They found it not as a picture, but as a pattern. Not as a nearby object, but as a shared behaviour. They followed the sideways drift, the radial plunge, the chemical clues, and the strange lack of ordinary disk rotation. They saw that many stars in the halo were not simply random wanderers, but remnants of a larger body that had fallen into the Milky Way long ago. To imagine the ancient collision, it helps to let go of the way collisions usually work in everyday life. When two cars collide, metal bends, glass breaks, people hear the impact and the whole event is over in seconds. When two galaxies collide, almost none of that familiar drama applies. There is no single crash. There is no hard surface. There is no sharp sound echoing across space, because space is not kind enough to provide air for dramatic effects. Instead, there is gravity, distance, and time. A galaxy collision is a slow rearrangement of millions or billions of stars, gas clouds, dark matter, and ancient orbits. It is less like two stones striking, and more like two great swarms passing through one another, pulling, stretching, and disturbing each other until the smaller swarm loses its old shape and becomes part of the larger one. The galaxy that became the Gaia Sausage did not meet the Milky Way as a little sparkle drifting politely at the edge. It was a real galaxy, a smaller companion with its own stars, its own dark matter halo, its own history of star formation, and its own path through the young universe. It may have looked like one of the dwarf galaxies we see around larger galaxies today, though not exactly like any single one we can point to. It was smaller than the Milky Way, but not so small that the Milky Way could absorb it without noticing. This was not the galactic version of brushing a crumb from a sleeve. It was more like a young city suddenly taking in another town, roads, buildings, people, noise, memories, and all. The larger place survives, but it is changed. The timing takes us far back. The merger is generally placed roughly 8 to 11 billion years ago, though astronomers continue refining the exact story as new data and models appear. That means it happened when the Milky Way was still young, long before the Sun formed about 4.6 billion years ago, long before Earth had oceans, long before the first cells, long before any creature could look up and give names to the stars. It was an early event in the life of our galaxy. At a time when the universe itself was younger, galaxies were still assembling, and the Milky Way had not yet settled into the more familiar spiral system we live in now. The galaxy we call home was still under construction, and this collision was one of the events that helped decide what kind of home it would become. Picture the young Milky Way not as a completed spiral with neat arms and a calm thin disk, but as a growing system. It had stars, gas, dark matter, and rotation, but it was still being shaped. Its disk may have been thicker, more turbulent, and more vulnerable to disturbance than the graceful image we often imagine. Around it stretched a dark matter halo, invisible but massive, helping hold the whole structure together. Nearby, smaller galaxies moved through the same gravitational neighbourhood. Some stayed distant for a time, some were pulled in. Some came close enough to be stretched and eventually lost. In a universe governed by gravity, distance is not always protection. A small galaxy can wander near a larger one and slowly discover that it is no longer entirely in charge of its own future. The Gaia Sausage progenitor, meaning the original galaxy before it was torn apart, likely approached on a highly elongated orbit. Instead of gently sliding into the Milky Way's rotation like a leaf joining a whirlpool, it plunged in more directly. This matters because the path of entry shaped the debris we see today. A galaxy falling in on a more circular orbit might leave stars with more rotation around the Milky Way. A galaxy falling in on a radial path, diving toward the centre, and then outward again, leaves stars on stretched, plunging orbits. That is the motion Gaia helped reveal billions of years later. The old collision did not simply leave material behind, it left a pattern of movement, a fingerprint written in the paths of stars. As the smaller galaxy entered the Milky Way's gravitational grip, tidal forces began the work. Tidal forces are not mysterious in principle. Earth's ocean tides happen because the Moon pulls slightly more strongly on the near side of Earth than on the far side. Across a galaxy, the same idea becomes enormous. The side of the dwarf galaxy closer to the Milky Way felt a stronger pull than the side farther away. Over time, that difference stretched the smaller system. Stars near the edges became easier to remove. Its dark matter halo was stripped. Its original structure loosened. With each close passage, the Milky Way peeled away more of it, like gravity patiently unthreading a sweater. Not quickly, not neatly, and probably without any concern for where the sleeves ended up. The smaller galaxy may have passed through or near the Milky Way's inner regions more than once. Each passage would have stirred the Milky Way and stripped more stars from the infalling system. The stars that once orbited together inside the dwarf galaxy were scattered into the larger halo. Some were thrown onto long eccentric paths that brought them inward and outward through the galaxy. Some became part of streams or overlapping debris clouds. Some may now pass relatively near the Sun in galactic terms, not because the Sun was there to witness the event, but because their orbits carry them through the broad region we occupy. The original galaxy disappeared as a separate object, but its stars kept travelling. It is important to pause on what disappeared and what did not. The galaxy's shape disappeared, its independence disappeared, its centre was disrupted. Its stars were no longer held together as one small galaxy. But the stars themselves did not vanish. Most of them kept shining, aging, and orbiting. A galactic merger is destructive to structure, not usually destructive to individual stars. The stars are so far apart that direct collisions between them are extremely rare. If you could stand on a planet around one of those stars during the merger, the night sky might change over immense stretches of time, but you would not necessarily see another star rushing straight at you. The danger would not be a star smashing into your system. The great change would be gravitational. Orbits would shift. The galaxy above you would slowly become a different galaxy. There may have been gas involved as well, and gas behaves differently from stars. Stars are like tiny independent travellers, each following gravity. Gas clouds can collide, compress, heat up, lose energy, and form new stars. If the incoming galaxy carried gas, or if its passage disturbed gas in the young Milky Way, the collision may have helped trigger a period of enhanced star formation. Some studies suggest the Gaia Sausage Enceladus merger may have been connected to changes in the Milky Way's thick disk and early star-forming history. That detail is still explored through models, stellar ages, and chemical measurements, but the general idea is clear enough for our quiet journey. A major merger does not only add stars, it can wake up gas, it can stir a disk, it can change the rhythm of a galaxy's growth. The disk of the Milky Way was especially important. Today we often speak of the Milky Way's thin disk and thick disk. The thin disk contains many younger stars, gas, dust, and the spiral arms where star formation continues. The thick disk is older, puffier, and made of stars whose orbits take them farther above and below the galactic plane. The existence of the thick disk has more than one possible explanation, and astronomers do not reduce all of it to one simple cause. But the Gaia-Enceladus Sausage merger is widely considered a major event that could have dynamically heated an early disk, meaning it stirred the motions of stars and helped produce a thicker, more vertically extended population. Heating here does not mean warmth in the ordinary sense. No one placed the Milky Way in an oven, which is probably for the best. It means the star's orbits became less flat and more energetic. Think of a thin disk of stars like a quiet flock moving mostly in the same plane. Then a smaller galaxy plunges through or near it, tugging with gravity. The stars do not stop being stars, they do not all fly apart, but their orbits are nudged. Some begin to move higher above the disk, some gain more random motion. The disk becomes puffier. It remembers the disturbance in the way its stars travel. Billions of years later, astronomers look at old stars in the thick disk and halo and ask, what stirred you? The answer may include the Gaia Sausage merger, one of the great early disturbances that helped shape the Milky Way into the layered structure we see today. The halo was changed too. The stellar halo of the Milky Way is faint compared with the disk, but it is rich in history. It contains old stars moving on orbits that are often tilted, elongated or less organized than disk orbits. The Gaia Sausage contributed a large amount of debris to the inner halo. This is one of the reasons the discovery was so important. It suggested that much of what we see in the inner halo is not simply a smooth ancient population formed in place, but the remains of a substantial accreted galaxy. Accreted is the polite scientific word. Swallowed is the dramatic word. Both point toward the same thing. The Milky Way grew by taking in another system, and the halo became a place where that system's stars continued to move. During the collision, dark matter was involved in a huge but invisible way. Every galaxy is thought to sit inside a much larger halo of dark matter. Matter we cannot see directly but infer from its gravitational effects. The Gaia Sausage galaxy would have had its own dark matter halo. As it fell into the Milky Way, that halo would have been stripped and mixed into the Milky Way's larger dark matter halo. We cannot see dark matter debris the way we see stars, which is rather inconvenient of it. But simulations suggest that mergers do not only rearrange visible stars, they also build and reshape the dark matter structure around galaxies. The stars are the glowing clues, but behind them is a much larger gravitational story. This is one of the quiet surprises of galaxy formation. What we see is only the bright part. The true mass and motion of a merger includes dark matter, gas, and gravity working together. A small galaxy does not fall into the Milky Way simply because its stars are attracted. The entire system, visible and invisible, is drawn in. Its dark matter halo helps determine how it moves, how long it survives, and how much damage it causes. Its stars are stripped and thrown into new orbits. Its gas may be removed or compressed. Its clusters may survive as dense little relics. By the time the merger is finished, the original galaxy is gone, but its ingredients have been sorted into the larger one in different ways. Some of those dense relics may be globular clusters. Globular clusters are old, tightly packed groups of stars, often containing hundreds of thousands of stars in a compact sphere. They orbit the Milky Way like ancient lanterns around the halo. Some globular clusters likely formed in the Milky Way itself, but others may have been brought in by smaller galaxies. The Gaia Enceladus Sausage event has been associated with a number of globular clusters whose orbits and age metallicity patterns suggest they came in with the merger. That is another way the ancient collision may still be around us, not only as individual stars but as surviving clusters, little bundled memories of the lost galaxy's system. The collision also changed our understanding of the Milky Way's biography. Before discoveries like this, it was tempting to imagine the Milky Way as a galaxy that formed fairly smoothly, gathering gas, forming stars and developing its disk in a mostly internal process. Mergers were known to happen, but the details of our own galaxy's merger history were harder to pin down. Gaia made it clearer that a major merger occurred early and left a strong signature. The Milky Way is not just a spiral that quietly grew by sipping gas from the cosmic surroundings. It also experienced a significant impact that shaped its halo and may have stirred its disk. The calm present sits on top of a complicated past. There is a strange comfort in the idea that even a violent cosmic event can become part of stability later. The Gaia Sausage merger may have been disruptive, but it did not prevent the Milky Way from eventually forming the Sun, the planets, and the conditions that led to life on Earth. In fact, the galaxy we live in is partly the result of that disruption. Its present structure, its halo populations, its thick disk, its mixture of stars, all belong to the story that came after. We often think of peace and disturbance as opposites, but in galaxies, long-term order can emerge after enormous disturbance. The Milky Way was shaken, stirred, and enlarged, then continued to evolve. Billions of years later, a small star formed in its disk, and around that star, a small planet eventually grew quiet enough for someone to fall asleep while hearing about galactic mergers. The universe does enjoy taking the scenic route. If we could speed up the collision into a viewable scene, the smaller galaxy might appear as a glowing knot moving toward the larger disk. Its shape would stretch under tidal forces. Long arms of stars might trail behind and ahead of it. The Milky Way's own disk might ripple, thicken and respond. Gas could flow inward or compress in places. Star formation might brighten certain regions. The dwarf galaxy would swing around, plunge again, lose more material and gradually dissolve. Over many orbits, its once separate identity would smear into the halo. Eventually there would be no obvious galaxy left, only debris spread through the Milky Way's gravitational field. Then billions of years would pass. The Sun would form. Earth would form. Life would begin. Humans would invent telescopes, space missions, and, for reasons known only to our species, the word sausage would end up attached to one of the most important mergers in our galaxy's history. That long delay between event and discovery is one of the most beautiful parts of the story, in a plain and practical way. The collision happened without witnesses from Earth, because Earth did not exist. The stars moved for billions of years without anyone naming their orbits. The evidence waited, not because the universe was trying to tell us something, but because physical traces persist. Motion persists. Chemistry persists. Age patterns persist. When the right instruments finally came along, the old event became readable. Astronomy often works like this. We cannot watch most cosmic history unfold directly, so we learn to read leftovers. Light from distant galaxies, cratered surfaces, ancient minerals, stellar motions. The universe is not quiet because nothing happened. It is quiet because the evidence is patient. The ancient collision changed the Milky Way forever because it added material, redistributed stars, helped build the halo, disturbed the early disk and marked a major stage in the galaxy's growth. It also changed the story we tell about where we are. The Milky Way is not only the galaxy that held the Sun, it is the product of earlier galaxies, some still visible as companions, others dissolved beyond ordinary recognition. The Gaia Sausage is one of those dissolved systems, not completely gone, not intact, but present in the motions of stars. It is part of the reason the halo looks the way it does. It is part of why some stars around us move on strange plunging orbits. It is part of the answer to how the Milky Way became large, layered, and complex enough to be our home. When we call this event ancient, it can sound distant enough to become unreal. 8 to 11 billion years is not a number the human mind can easily hold. We can say it. We can write it. We can place it on a timeline, but to feel it is almost impossible, so maybe think of it this way. The collision was already old when the Sun was born. It was already part of the Milky Way's deep background before Earth cooled, before the Moon settled into its familiar place in the sky, before the first oceans reflected sunlight. The stars from that smaller galaxy had already been folded into new paths before our entire solar system began. By the time humans looked up and saw the Milky Way as a pale band, the swallowed galaxy had been around us for longer than Earth itself had existed. That is why the Gaia Sausage is not just a story about destruction, it is a story about inheritance. The Milky Way inherited stars, clusters, dark matter and motion from another galaxy. It inherited a disturbance that helped shape its structure. It inherited scars that do not look like scars until you know how to measure them. And now we inherit the knowledge of it, the awareness that the galaxy above us is not one simple thing. It is a layered body of histories, some born here, some brought here, some broken apart and mixed in so deeply that only their movement gives them away. The stars left behind by the Gaia Sausage are not gathered in one neat corner of the sky. They are not arranged like a little broken constellation, waiting for someone to draw lines between them and say, "There, that is the old galaxy." By now, too much time has passed for anything that simple. The original galaxy has been stretched, shredded, mixed, and folded through the Milky Way for billions of years. Its shape is gone, its borders are gone, its center is gone. But many of its stars are still here, moving through the wide, faint halo of our galaxy, following long paths that tell a very old story if we know how to read them. They are strange, not because they look strange to the eye, but because they behave strangely. They are ordinary points of light with extraordinary histories, like quiet travellers in a crowd who happen to be carrying the last memory of a country that disappeared before the sun was born. The Milky Way's halo is not the bright band most people picture when they think of our galaxy. The bright band is the disk, where most of the stars, gas, dust and spiral structure live. That is where the sun is. That is where most of the familiar galactic traffic moves around the centre in a shared rotation. The halo is different. It is larger, dimmer, older, and much more sparsely populated. It surrounds the disk in a broad, faint, roughly spherical region, though not a perfect sphere, because galaxies rarely behave like geometry homework. The halo contains old stars, globular clusters, stellar streams, and a great deal of dark matter. If the disk is the busy city, with traffic lanes, streetlights, nurseries, dust clouds, and active neighbourhoods, the halo is the old countryside around it, quiet at first glance, but filled with ruins, old roads, and signs that people passed through long ago. These halo stars are often very old. Many formed early in the history of the Milky Way, or came from smaller galaxies that were absorbed long ago. They tend to have lower amounts of heavy elements than younger disk stars, because they were born before many generations of stars had enriched the galaxy with iron, oxygen, magnesium, calcium, and all the other elements forged and scattered by stellar lives and deaths. Astronomers call everything heavier than helium a metal, which can sound odd when it includes things like oxygen. So if you ever hear an astronomer say a star is metal poor, they do not mean the star has misplaced its toolbox. They mean it formed from gas that had not yet been enriched by many earlier stars. In the halo, many stars carry that ancient chemical simplicity, and some carry patterns that point not to the Milky Way's own early gas, but to smaller galaxies with different histories. The Gaia Sausage stars belong to this halo population, but they stand out from many other halo stars because of their orbits. Their paths are highly elongated. They plunge inward toward the centre of the Milky Way, and then swing outward again into the halo. Instead of moving around the galaxy in a calm, circular flow, they travel on stretched, eccentric routes, almost as if they are still echoing the path of the galaxy that brought them here. If the disk stars are moving like dancers circling a ballroom, these stars are moving like guests who entered through one door, crossed the room, disappeared into the hallway, and then came back through the same strange route again and again. It is not random motion, it is old motion. It is the after effect of a galaxy that fell in deeply and was pulled apart. This kind of orbit is one of the main reasons astronomers could identify the Gaia Sausage. The stars are not strange because they are especially bright. Many are faint. They are not strange because they all sit together in a visible cloud. They are spread through the inner halo. What makes them unusual is their shared way of moving. They have strong radial motion, meaning they move significantly toward and away from the galactic centre. They do not have much of the orderly rotation that disk stars usually carry. In velocity diagrams, they form a broad elongated structure, the famous sausage shape, not in physical space but in the space of motion. That distinction is important. If you went outside tonight, looked up and searched for a sausage-shaped glow, you would have a long and disappointing evening, though perhaps a memorable one. The shape is in the data. A star's orbit is like a memory written in gravity. It does not remember in the way you remember a childhood room, or the smell of rain on pavement, but it carries information about where it has been, and what forces have acted on it. A star born in the Milky Way's disk usually begins with the motion of the gas cloud that formed it. That gas was already rotating around the galaxy, so the star inherits much of that rotation. A star from a dwarf galaxy that crashed into the Milky Way inherits a different story. It was once orbiting inside its own smaller galaxy. Then, as that galaxy fell in and was torn apart, the star was released into the Milky Way's gravitational field. Its new orbit depended on the path of the infalling galaxy, the mass of the Milky Way, the timing of the stripping, and the long gravitational mixing that followed. Billions of years later, that orbit is still not quite like a native disk star's orbit. The halo is the perfect place for such leftovers to hide. It is not crowded in the same way the disk is crowded. Its stars are spread far apart, moving on large tilted paths, often reaching high above and below the galactic plane. Some pass through the inner regions of the Milky Way, then travel back out to great distances before falling inward again. These are not tidy little circles. They are long loops, plunges, arcs, and returns. The Gaia Sausage stars in particular can be thought of as the debris of a galaxy whose original orbit was almost head-on compared with the Milky Way's rotation. That is why so many of its stars now move along similar in and out routes. The parent galaxy was not gently stirred into the disk. It struck deep into the Milky Way's gravitational body and left its stars on paths that still show that direction. There is something almost haunting about a star that looks perfectly ordinary but belongs to a vanish system. Imagine one of these stars passing through the halo. It may be older than the Sun by many billions of years. It may have formed in a small galaxy with a sky very different from ours. Around it, perhaps, there were other stars from the same dwarf galaxy, clusters, gas clouds, maybe a central concentration of light. Then the Milky Way's gravity took over. The small galaxy stretched. Its stars were pulled away. The view from that star's imaginary neighbourhood would have changed slowly, over cosmic time, as its old galaxy dissolved and the Milky Way grew around it. Now that star is part of our galaxy's halo, but its orbit still whispers that it came from somewhere else. Of course, stars do not feel exile. They do not miss their original galaxy. They do not drift through the halo thinking, well, this neighbourhood has changed since I was young. That would be charming, but stars are very committed to being balls of plasma rather than sentimental historians. The history is in our interpretation. We look at their motion and chemistry, and we say this star likely formed outside the Milky Way. This star was accreted. This star may belong to Gaia Sausage. We build the story from measurements. Still, it is hard not to feel a little wonder at the idea that the night sky contains stars that began their lives in a galaxy that no longer exists. The chemical side of the story adds another layer. The Gaia Sausage stars are generally old and relatively metal-poor compared with many stars in the Milky Way disk, but they are not all identical. Their chemistry suggests they came from a dwarf galaxy, large enough to form stars over time and enrich itself, but not as massive or chemically evolved as the Milky Way. This is one reason the progenitor was not thought to be a tiny star cluster or a very small fragment. It was a galaxy with its own enrichment history. Its supernovae added heavier elements to its gas. Its later generations of stars carried those elements. Then the galaxy was absorbed, and those chemical records were carried into the halo. A star's atmosphere becomes, in that sense, a tiny preserved sample of its birthplace. Astronomers can measure these chemical fingerprints by taking spectra. Starlight, when spread into a spectrum, contains dark lines, where specific elements absorb light at particular wavelengths. These lines reveal what elements are present in the star's outer layers. From this, astronomers estimate metallicity and abundance ratios, such as how much iron a star has compared with hydrogen, or how much magnesium it has compared with iron. These details may sound small, almost too small for a galaxy-sized story, but they are powerful. Motions can identify a group. chemistry can tell us whether that group shares a plausible origin. When stars move strangely and also carry chemical patterns consistent with a dwarf galaxy, the case becomes much stronger. The halo also contains globular clusters that may be linked to the same ancient merger. Globular clusters are dense balls of old stars, packed so tightly that their centers can look like piles of diamond dust in telescope images. Some globular clusters likely formed in the Milky Way itself, but others probably arrived with accreted galaxies. The Gaia Sausage event appears to have brought some clusters into the Milky Way, or at least researchers have identified clusters whose orbits and properties are consistent with that origin. These clusters are like more visible relics among the scattered debris, compact enough to survive while their parent galaxy dissolved around them. If individual stars are loose pages from the Lost Galaxies book, globular clusters are whole paragraphs still bound together. There are also stellar streams in the Milky Way halo, long trails of stars pulled from dwarf galaxies or star clusters. Some streams are younger and more distinct, like fresh scratches on the galactic surface. Others are older and more mixed. The Gaia Sausage debris is not a simple narrow stream, because the merger happened so long ago and the original galaxy was so thoroughly disrupted. Its stars have wrapped and mixed through the inner halo over many orbits, but the general idea is related. When the Milky Way pulls apart another system, the stars do not instantly become random. For a time, they trace the path of the disruption. Over billions of years, those traces blur, but the deeper orbital patterns can remain. The halo is full of these hints, some sharp, some faded, some still being argued over in the calm but determined manner of scientists looking at complicated graphs. The stars of the Gaia Sausage also help us understand the shape and mass of the Milky Way itself. A star's orbit depends on the gravitational field it moves through. If you can measure many halo stars and their paths, you can infer something about the mass distribution of the galaxy, including the dark matter halo. In this way, accreted stars become test particles, natural probes moving through the Milky Way's gravitational landscape. They are not only evidence of an old merger, they are tools for studying the present galaxy. The Milky Way swallowed their parent system, and then, much later, we used their motions to learn more about the galaxy that swallowed them. There is a kind of cosmic irony there, gentle but real. From our position in the disk, the halo can feel remote. We do not live in the halo. The sun stays near the galactic plane, moving around the centre with other disk stars. But halo stars can pass through the region near the sun, as their orbits carry them inward. This is why astronomers can study some of them in detail from relatively nearby samples. They are not all distant specks at the outer edge. Some are passing through our part of the Milky Way's broader neighbourhood. That makes the Gaia Sausage feel less like a faraway fossil and more like something woven around us. The remains are not neatly outside. They cross through the galaxy, through its inner halo, sometimes through regions close enough for careful measurement. These stars remind us that the Milky Way is not one population, but many overlapping populations. Thin disk stars, thick disk stars, bulge stars, in situ halo stars, meaning stars formed within the Milky Way system, accreted halo stars, meaning stars formed in smaller galaxies and later brought in, streams from disrupted clusters, debris from dwarf galaxies, groups with names and groups still being discovered. The galaxy is less like a smooth bowl of soup and more like a stew with ingredients added at different times, from different places, some dissolved, some still recognizable, and all of it now called by one name. A slightly hungry metaphor perhaps, but given that this entire story involves a galactic sausage, we have already crossed that bridge. The strange motion of these stars also tells us about the violence of the original event. Highly radial orbits do not come from a quiet, gradual blending of two perfectly aligned systems. They suggest a collision in which the smaller galaxy plunged deeply into the Milky Way. Its stars were thrown into orbits that carry them close to the galactic centre and far outward again. This creates a population that is dynamically hot, moving with large random speeds compared with the ordered disk. The halo, in this sense, is not just old, it is stirred. The Gaia Sausage stars are part of that stirred population, a reminder that the young Milky Way was shaken by something large enough to leave a permanent orbital signature. The word permanent should be used gently, because in astronomy, very little is permanent in an absolute sense. Over even longer times, orbits can change. The Milky Way will continue to evolve. Future mergers, including the eventual encounter with Andromeda, will transform the galaxy beyond recognition. But on the timescale between the Gaia Sausage merger and today, the signature has lasted long enough to be measured. That is remarkable. A galaxy was torn apart, its stars scattered, the Milky Way continued growing, the Sun formed, Earth formed, life appeared, humans looked up, and still the old stars kept enough of their shared motion for us to identify them. The universe may be messy, but it is not careless with all of its evidence. There is also a human lesson in the difficulty of seeing these stars for what they are. For a long time, they were hiding in plain sight. They were in the catalogues, in the sky, part of the halo, part of the Milky Way. But without the right measurements, they did not stand out as a single ancient population. It took Gaia's precision to connect their motions. This happens often in science, something is present before it is understood. The evidence exists, but the pattern is invisible until a new instrument, a new method, or a new idea allows us to see it. The Gaia Sausage was not created by discovery. It was revealed by discovery. The stars were already moving that way. We simply learned to notice. If you imagine the Milky Way as a great old house, the halo stars are like objects stored in the attic. Some were placed there when the house was first built. Some were inherited from relatives. Some came from other houses that were dismantled. Some have been there so long no one remembers how they arrived. Then one day, someone opens the attic, checks the labels, studies the wood grain, notices the style, and realizes that a whole set of objects came from the same lost place. That is what Gaia helped astronomers do. It opened the attic of the galaxy. It showed that many halo stars were not random old objects, but the remains of a shared event. The stars themselves keep moving. Even now, while you listen, while the room around you is still, while your own clock counts minutes in a very ordinary way, those stars are travelling on enormous paths through the Milky Way. Some are moving inward, some are moving outward, some are passing above or below the disk. Their motions are not hurried by human standards, because the distances are too large for ordinary comparison, but they are fast in physical terms. Stars orbit the galaxy at speeds measured in hundreds of kilometers per second. A halo star can cross vast regions of space while seeming perfectly fixed in the sky from our short-lived perspective. We see a point of light. The galaxy feels an orbit. That difference between appearance and reality is at the heart of the Gaia Sausage story. The sky looks still, but it is moving. The Milky Way looks peaceful, but it has merged and consumed. A star looks local, but it may have come from another galaxy. The halo looks faint, but it contains one of the most important records of the Milky Way's formation. Everything depends on learning which kind of looking is needed. Our eyes are good at beauty, instruments are good at precision. Science is the patient conversation between the two. The name sounds almost unserious at first, does it not? Gaia Sausage. After all this talk of ancient collisions, halo stars, dark matter, and the deep construction history of the Milky Way, we arrive at a name that seems as if it wandered in from a breakfast table. Space is full of grand names: Andromeda, Cassiopeia, Sagittarius, Enceladus, Orion. Names that feel carved from mythology, names that seem to belong to marble statues and old maps with sea monsters in the corners. Then, quietly, astronomy opens the door and says, "Here is one of the most important mergers in the history of our galaxy, and we have called it the Sausage." It is hard not to smile a little. The universe may be vast and ancient, but scientists are still human beings looking at a shape in a graph and occasionally thinking, well, that looks familiar. But the name is not random. It is not a joke pasted onto a serious discovery for decoration. It grew out of the way the evidence was found. Each part of the full name, Gaia Sausage Enceladus, points to a different piece of the story. Gaia points to the spacecraft that helped reveal the stars. Sausage points to the unusual shape those stars made in velocity space. Enceladus points to the mythological name used by another research group to describe the same great accreted galaxy. So, although the name sounds a little odd, it is actually a compact history of the discovery. It tells us who helped find it, what the data looked like, and how astronomers understood the ancient galaxy that fell into the Milky Way. Not bad for a name that also sounds like something you might accidentally order at a very unusual cafe. Let's begin with Gaia, because Gaia is the reason the hidden pattern became visible. Gaia is a space observatory launched by the European Space Agency to map the Milky Way with extraordinary precision. Its job is not mostly to take dramatic pictures. It is doing something more patient and in its own way more powerful. Gaia measures the positions, distances and motions of stars. It watches them again and again, building a detailed moving map of our galaxy. This is called astrometry, and it's one of those fields that can sound quiet until you realize what it can do. By measuring tiny shifts in the positions of stars, Gaia can help astronomers work out how far away they are and how they are moving through space. A tiny angle on the sky, measured carefully enough, can become a distance. A tiny drift, repeated across years, can become a velocity. And when you do this for huge numbers of stars, the Milky Way stops being just a band of light and becomes a flowing system. Gaia is named after the Greek goddess of Earth, which is a fitting name for a mission that helps us understand the wider home around Earth. In mythology, Gaia is a mother figure, a beginning point, a source. In astronomy, Gaia became a kind of patient surveyor, quietly measuring the stellar family around us. It's a lovely contrast. The mission does not roar through the galaxy or chase one spectacular target. It measures, it counts, it returns to stars again and again. It notices small things, and because it notices small things so well, it reveals very large stories. A galaxy eaten long before the sun existed did not announce itself with a bright sign. It revealed itself through the slow, careful measurement of star motions. The sausage part comes from those motions. It does not mean the old galaxy looked like a sausage in the night sky. It does not mean there is a long sausage-shaped trail you can see with a telescope if you know where to look. The shape appeared in a diagram of velocities. Astronomers plotted how certain halo stars were moving, especially stars that were not travelling in the orderly rotation of the Milky Way's disk. These stars were plunging inward and outward through the galaxy on very elongated orbits. When their velocities were displayed in a certain way, they formed a stretched, sausage-like shape. The name may be playful, but the pattern was serious. It showed that many stars shared a common kind of motion, as if they came from the same disrupted system. Velocity space is worth sitting with for a moment, because it is the little doorway through which the name enters. In ordinary space, we describe where things are. This star is here. That star is there. This cluster is above the galactic plane. That stream stretches across the halo. But in velocity space, we describe how things are moving. It is a map of motion rather than location. Imagine a room full of people. If you draw where everyone is standing, you get a floor plan of the room. But if you draw how fast everyone is moving and in what direction, you get something different. People walking toward the door group together in one part of the motion map. People circling the room group somewhere else. People standing still gather near the centre. Now imagine that a large group of people, scattered all over the room, turn out to be moving with the same strange pattern. You might not have noticed them by position, but in motion, their shared origin becomes obvious. That is what happened with the Gaia Sausage stars. Physically, they were spread out through the halo. They were not sitting in one easy clump. But when astronomers looked at how they moved, a shared structure appeared. Many had strongly radial orbits. Radial in this context means their motion was mostly inward and outward, relative to the centre of the Milky Way. They were not calmly circling the galaxy with the disk. They were diving in and out, crossing the inner regions and swinging back into the halo. This made sense if their parent galaxy had crashed into the Milky Way on a strongly radial path. In other words, the smaller galaxy came in on a kind of plunging orbit, and when it was torn apart, its stars kept the imprint of that motion. The sausage shape in the diagram came from plotting components of velocity, often the radial motion against the rotational motion around the galaxy. Disk stars tend to have strong rotation because they are part of the Milky Way's spinning disk. The sausage stars had much less organised rotation and much more inward-outward motion. This created that elongated blob in the data. The exact technical details can become quite mathematical, but the basic idea is gentle enough. If you sort stars by how they move, the old swallowed galaxy shows up as a stretched family of motions. The sausage is not a thing floating in space. It is the shadow of an event cast into a diagram. That may sound less romantic than a glowing object in the sky, but in some ways it is more interesting. It means the name came from the evidence itself. The data had a shape. Astronomers gave that shape a memorable nickname. Science often does this. It creates terms that are practical, visual, and sometimes unexpectedly plain. The bullet cluster is named because of its shape and motion. The tadpole galaxy has a long tail. The sombrero galaxy looks like a wide-brimmed hat. The cosmic horseshoe, the cigar galaxy, the antennae galaxies, these names come from the human habit of recognizing familiar forms in strange places. The Gaia Sausage belongs to that tradition, though perhaps with less dignity at a formal dinner. And then we have Enceladus. The name Gaia Enceladus was introduced by researchers who saw the same ancient merger in Gaia data and described the accreted galaxy with a mythological name. In Greek mythology, Enceladus was one of the giants, and importantly a child of Gaia. That connection made the name appealing. Gaia the mission revealed the evidence, and Enceladus, the child of Gaia, represented the ancient galaxy whose remains were found. It also suggested size and importance. This was not a tiny bit of debris, it was a major event, a giant in the early history of the Milky Way. When combined with the sausage-shaped velocity signature found by other researchers, the names became linked. Gaia Enceladus, Gaia Sausage, Gaia Sausage Enceladus. Different names, same broad ancient merger, seen through slightly different approaches and traditions. There is a useful lesson in the fact that one event can have more than one name. Science is not always as tidy as a textbook makes it look. Discoveries often happen through multiple teams, different data selections, different methods, and different names that later turn out to be describing related parts of the same story. One group might emphasize the motion pattern and call it the Gaia Sausage. Another might emphasize the accreted galaxy as a mythological remnant and call it Gaia Enceladus. Later, the combined name Gaia Sausage Enceladus helps acknowledge both lines of work. It may be a bit long, and it may not roll off the tongue as smoothly as Orion, but it carries the history of how the idea developed. It is a name with layers, rather like the Milky Way itself. The slightly funny name also makes the discovery easier to remember. That may sound trivial, but memory matters in science communication. If astronomers had called it something like the high eccentricity radially anisotropic accreted inner halo component, fewer sleepy listeners would make it through the sentence, and several perfectly good cups of tea might go cold. The formal descriptions still exist in papers, of course, because precision matters, but a nickname like Gaia Sausage gives people a handle. It lets the story travel. It makes a complex event easier to discuss without losing the core idea. A galaxy fell in, its stars ended up on strange plunging orbits, and in the motion data, they made a sausage-like pattern. The humour of the name also helps soften the scale of what it represents. We're talking about a collision that helped shape the Milky Way's inner halo and may have disturbed the early disk. We're talking about a dwarf galaxy that was torn apart across billions of years. We're talking about stars that have been moving through the halo since before the Sun existed. It is a huge, ancient, almost impossible thing. And then the name gives us a small human foothold. Sausage. Something familiar. Something ordinary. It reminds us that astronomy is done by people, and people bring their eyes, metaphors, jokes, and hunger into the way they describe the universe. Even when studying cosmic archaeology, someone still has to look at the graph, but the name should not make the object seem less important. The Gaia Sausage, or Gaia Enceladus, is often described as one of the last major mergers of the Milky Way. It was large enough to leave a major imprint. Its debris contributes to the stellar halo. Its stars move differently from most disk stars. Its merger may have played a role in shaping the thick disk and early structure of the galaxy. This was not a minor drizzle of stars from a tiny disrupted cluster. It was a major accretion event. The funny name sits on top of a serious fossil. Like finding an ancient monument and discovering someone nicknamed it the Big Old Pancake. You may smile at the name, but the stones are still ancient. The Gaia part also reminds us how new this understanding is. The merger happened billions of years ago, but our ability to identify it clearly depends on modern precision data. Before Gaia, astronomers knew the Milky Way had a complex halo. They knew about accretion, dwarf galaxies, and stellar streams. But Gaia provided a leap in the quality and quantity of stellar motion measurements. When those measurements were combined with ground-based spectroscopic surveys and careful modelling, the hidden structure became much more obvious. The old galaxy had been around us all along, but without Gaia's map, it was like a message written in letters too small to read. It is worth noticing that Gaia did not find the sausage by seeing the past directly. There is no video of the ancient collision. No telescope has a recording from 10 billion years ago showing the dwarf galaxy falling into the Milky Way with dramatic music, though if it did, I suspect the soundtrack would be very slow. Gaia found the aftermath. It measured the present-day positions and motions of stars. Astronomers then reconstructed the likely past from those present clues. This is how much of astronomy works. We are latecomers. We arrive after the explosions, after the mergers, after the first stars, after the planets form. Then we read light, motion, chemistry, and structure to figure out what happened. The sausage name is therefore a reminder that the past can hide in unexpected coordinates. If we only look at where stars are, the remnant is hard to isolate. If we look at how they move, the old event becomes clearer. The lost galaxy is not a visible object anymore because the Milky Way has mixed it into itself. But it does not fully erase the motion. That is why the nickname is so tightly connected to velocity space. The swallowed galaxy survives as a moving signature. Its stars are no longer arranged as their own galaxy, but many still share the orbital character of their infale. In ordinary space, the old galaxy is dissolved. In motion space, it still has a shape. That idea has a quiet beauty without needing to dress it up too much. A thing can be gone in one sense and present in another. The Gaia Sausage galaxy is gone as an independent system. You cannot travel to it as a separate dwarf galaxy. You cannot draw its original outline on the sky, but its stars remain, its clusters may remain, its chemical history remains, its motion pattern remains. The Milky Way ate it, but digestion in galaxies is never perfect. Gravity mixes, stretches and folds, but it leaves traces. The name points directly to one of those traces. Enceladus adds yet another feeling to the story because it gives the swallowed galaxy a kind of identity. Sausage describes the data pattern. Enceladus describes the galaxy as a former body, a giant child of Gaia, a system that once existed before being broken apart. One name comes from a graph. The other comes from myth. Together, they fit astronomy surprisingly well. The field is always balancing measurement and imagination. Not imagination in the sense of making things up, but imagination in the sense of seeing what the measurements imply. Data tells us there are stars moving this way. Interpretation tells us they likely came from a large ancient dwarf galaxy. A name helps us hold both thoughts at once. The name also gives us a way to talk about scale. If the galaxy was large enough to be called a giant in the Milky Way's merger history, then it was not merely a loose group of stars. It had mass, gravity, dark matter, and a chemical life of its own. It likely formed stars for a long time before merging. Its stars were not all identical. Some were older, some younger, some more chemically enriched than others. It may have carried globular clusters. It may have had gas. It had a story before it became part of our story. Calling it Gaia Enceladus helps keep that in mind. Calling it the Gaia Sausage helps remind us how we found the remains. The full name, slightly awkward as it is, preserves both the lost galaxy and the evidence trail. Perhaps the funniest part is that the name becomes less funny the more you understand it. At first, Gaia Sausage sounds like a cosmic joke. Then you learn that Gaia is the spacecraft, that the sausage is a velocity space structure, that Enceladus is the mythological identity of the accreted galaxy, and suddenly the name becomes sensible. Still unusual, yes. Still not something you expect to hear in a quiet documentary voice at bedtime. But sensible. It is not random whimsy. It is a map of the discovery compressed into a phrase, and it is also very human. We often understand the unknown by comparing it to the known. Ancient people looked at star patterns and saw hunters, animals, queens, scorpions, and bears. Modern scientists look at data plots and sometimes see sausages. The tools have changed. The sky has become more precise. The mathematics has become deeper, but the basic human impulse remains. We see patterns. We name them. We use the name to return to the pattern later and tell others what we found. A name is not the discovery itself, but it is the handle by which the discovery can be carried. The Gaia Sausage name also helps prevent a simple misunderstanding. Without explanation, someone might imagine the Milky Way literally ate something shaped like a sausage. It did not. The original galaxy may have been more like a dwarf galaxy, perhaps roughly spheroidal or irregular before disruption, though its exact appearance is difficult to reconstruct. The sausage shape is the debris in motion, not the original body in space. This distinction matters because it shows how deeply the system has been transformed. The old galaxy's visible form has been erased. What we see now is a dynamical remnant, a population of stars whose velocities still carry the imprint of the merger. So the name is really a small doorway into the method of galactic archaeology. First, Gaia measures the stars. Then astronomers identify a strange elongated pattern in how some halo stars move. Then they connect that pattern to a major accreted dwarf galaxy, also known as Enceladus. Then they compare motions, chemistry, ages, and simulations to build a picture of the merger. The nickname sits at the entrance, but behind it is a whole chain of evidence. It is not just cute, it is useful. By now, the name Gaia Sausage Enceladus has become part of the Milky Way's modern family history. It sits alongside other accreted structures and merger remnants that Gaia has helped reveal, reminding astronomers that our galaxy formed through a complex sequence of events. The Milky Way has a family tree, though not the neat kind printed in a genealogy book. It is more tangled. Some branches broke, some merged. Some were absorbed so thoroughly that only chemical and orbital traces remain. Gaia has helped identify those branches, and Gaia Sausage Enceladus is one of the largest and most important of them. There is a pleasant irony in the fact that one of the Milky Way's most violent ancient events now has a name that can make people laugh. Maybe that is appropriate for a bedtime science story. The universe can be overwhelming if every name sounds grand and severe. A little plainness helps. The Gaia Sausage reminds us that science is precise but not always solemn. It can measure billion-year-old collisions and still allow room for a slightly ridiculous nickname. It can speak of dark matter, halos, radial anisotropy, accreted debris, and then point to a plot and say, sausage. Somewhere in that mixture of accuracy and humour, the story becomes easier to hold. And as we hold the name more carefully, we can begin to look beyond it. If Gaia Sausage Enceladus was once a real galaxy, then what was it like before the Milky Way tore it apart? How many stars did it have? What kind of shape did it carry? Did it resemble dwarf galaxies we see today around the Milky Way or Andromeda? Did it have clusters, gas, old red stars, younger blue ones, a slow chemical history written into each generation? Before the Milky Way tore it apart, the galaxy we now call Gaia Sausage Enceladus was not a motion pattern in a diagram. It was not a fossil population in the halo. It was not a name in a research paper, or a funny nickname attached to a stretched shape in velocity space. It was a real galaxy. Smaller than the Milky Way, yes, but still a galaxy in its own right, with stars of different ages, a surrounding halo of dark matter, possibly gas, dense star clusters, and a long history before it ever fell into the larger system that would eventually become our home. It had its own gravity. It had its own centre. It had its own slow internal life. Then, over billions of years, that life was interrupted, pulled apart, and folded into the Milky Way so completely that today we have to reconstruct it from clues left behind in stars. This is where the story becomes both exciting and careful, because we cannot simply take a photograph of the lost galaxy before the merger. There is no ancient image waiting in a cosmic archive, no little before and after panel, with one side saying, "Here is the dwarf galaxy in its youth," and the other saying, "Here it is after the Milky Way got peckish." Astronomy rarely gives us such convenient paperwork. The original galaxy is gone as a separate object. Its stars are scattered. Its dark matter has mixed into the larger halo. Its gas, if it still had much gas at the time of merger, was stripped, heated, consumed or transformed long ago. So when astronomers ask what it may have looked like, they're not guessing randomly. They are rebuilding a picture from motion, chemistry, ages, simulations and comparisons with dwarf galaxies we can still observe today. The first thing to understand is that it was probably a dwarf galaxy, but the word dwarf can be misleading. In everyday speech, a dwarf sounds small, almost tiny, but in astronomy, a dwarf galaxy can still contain hundreds of millions or even billions of stars. It can have a dark matter halo far more massive than its visible parts. It can form stars for billions of years. It can have globular clusters, chemical enrichment, and a complicated history of its own. Calling Gaia Sausage Enceladus a dwarf does not mean it was a little sprinkle of stars. It means it was smaller than a giant spiral galaxy like the Milky Way. Compared with us, it was small. Compared with a human being or a planet or even a star cluster, it was enormous beyond any comfortable comparison. Estimates vary, but the lost galaxy may have had a stellar mass somewhere around hundreds of millions, to perhaps over 1 billion times the mass of the Sun. That is only the mass in stars, not counting dark matter. Its total gravitational presence would have been much larger. When it met the young Milky Way, the Milky Way itself was smaller than it is today, so the difference between them was not as extreme as it would be now. This is why the merger mattered so much. A galaxy that seems modest compared with the present-day Milky Way could have been a very serious intruder to the Milky Way of 10 billion years ago. It was not a pebble hitting a mountain. It was more like a large boulder striking a growing hill that had not yet settled into its final shape. What would that galaxy have looked like? We have to imagine something much less grand than the Milky Way's broad spiral disk, but still structured. Many dwarf galaxies are irregular or spheroidal rather than beautiful spirals. Some have clumpy star-forming regions, some are faint and diffuse, some are gas-rich, some are old and quiet. Gaia Sausage Enceladus may have looked like a small, somewhat irregular or compact dwarf system, with older stars spread through it, and perhaps younger stars forming from gas before its fall into the Milky Way. It may have had a brighter central region, not necessarily a dramatic nucleus, but a denser heart where more stars gathered. Around that, its stars would have thinned outward, held in place by the galaxy's own dark matter halo. The dark matter halo is important because it would have given the small galaxy most of its gravitational mass. If you could see only its stars, you might think of it as a modest little island of light, but if you could feel its gravity, you would notice a larger invisible body around it. Dark matter does not shine, does not form bright clouds, does not politely outline itself for telescopes, and generally refuses to make things easy. Yet it shapes galaxies. It helps them hold on to stars and gas. It affects how they orbit larger galaxies and how long they survive before being stripped apart. The lost galaxy's dark matter halo would have been the first thing the Milky Way's gravity began to peel away, long before the last visible stars were scattered. If the galaxy had gas when it approached the Milky Way, that gas may have made it look more alive. Gas is the material from which new stars form. A gas-rich dwarf can contain bright blue young stars, glowing nebulae, and patchy, star-forming clouds. A gas-poor dwarf looks quieter, older, redder, and dimmer. Which description fits Gaia Sausage Enceladus best is not perfectly certain, because by the time we study the debris today, the original gas is long gone, but its stars show that it had a real chemical history. It formed stars long enough for earlier generations to enrich the gas with heavier elements. That suggests it was not a single ancient burst and then nothing. It had time to evolve, to recycle material, to build stars from gas that had been touched by previous stars. This chemical history is one of the strongest tools for reconstructing the lost galaxy. Stars born early in the universe formed from gas that had very few heavy elements. Later stars formed from gas enriched by supernovae and stellar winds. So by studying the metallicity of Gaia Sausage Enceladus stars, and by comparing elements like iron, magnesium, aluminum and manganese, astronomers can estimate the kind of environment where they formed. The lost galaxy seems to have been less chemically enriched than the Milky Way disk, but more enriched than very tiny dwarf systems. That puts it in an interesting middle range. It was big enough to form many stars and enrich itself, but small enough to be swallowed. You might picture its stars in layers of age and chemistry. The oldest stars would have been metal poor, formed when the galaxy's gas was still almost fresh from the early universe. Later generations would have carried more heavy elements after supernovae exploded and returned enriched material to the interstellar medium. In a living dwarf galaxy, those different populations might not have been perfectly mixed. The centre might have held somewhat more enriched stars, while the outer regions might have contained older, more metal-poor stars. Some recent research explores whether Gaia Sausage Enceladus once had a metallicity gradient, meaning a pattern where the chemical richness changed with distance from its centre. The merger would have blurred that pattern, like stirring ink into water, but perhaps not erased every trace. If you could stand far outside the Milky Way billions of years ago and watch this smaller galaxy before the collision, it may have appeared as a faint, uneven smudge of starlight, perhaps not bright enough to impress someone expecting a grand spiral. But with a powerful telescope you might have seen structure, a denser middle, a softer outer glow, maybe knots of star formation if gas remained. Around it, invisible dark matter would have extended far beyond the visible stars. Dense globular clusters may have orbited it, little ancient beehives of stars, some of which may have survived the merger and now orbit within the Milky Way. Those clusters, if they truly came in with Gaia Sausage Enceladus, are among the most tangible remnants of its old system. They are compact enough to remain bound even after the larger dwarf galaxy was broken apart. This is a useful point, because when a galaxy is torn apart, not everything dissolves in the same way. Loose stars are stripped and spread out. Gas is disturbed and lost. Dark matter mixes into the larger halo. but dense globular clusters can survive as self-contained objects. They may continue orbiting long after their parent galaxy is gone. So if some Milky Way globular clusters came from Gaia Sausage Enceladus, they are like sealed jars from a vanished shipwreck, still carrying part of the original cargo. The ship itself is gone. The sea has scattered the planks, but a few hard objects remain. The lost galaxy may have resembled some dwarf galaxies around the Milky Way or Andromeda, though no present-day dwarf is a perfect match. The Fornax dwarf spheroidal galaxy, for example, is a substantial dwarf companion with globular clusters and a long star formation history. The Sagittarius dwarf is currently being disrupted by the Milky Way and shows us what tidal destruction can look like while it is still happening. The Large Magellanic Cloud is much more massive and still gas-rich, a brighter and more dramatic companion. Gaia Sausage Enceladus may have sat somewhere in this broad family of dwarf systems, not identical to any of them, but understandable through comparison. It was a smaller galaxy living near a larger one, and that is always a risky neighbourhood. The risk came from gravity. As Gaia Sausage Enceladus fell toward the young Milky Way, the larger galaxy's tidal pull would have begun to distort it. Before the final destruction, the dwarf may have grown stretched and lopsided. Its outer stars would have been stripped first, forming tidal tails. These tails are long streams of stars pulled ahead of and behind the galaxy along its orbit. From far away during the early stages of disruption, the dwarf might have looked like a small glowing body with faint arms trailing from it, like a comet made of stars. Not a comet in the icy sense, of course. No dusty tail blown by sunlight. This would have been a gravitational tail made of stars gradually losing their old membership. With each close passage around the Milky Way, the dwarf galaxy would have lost more of itself. Its dark matter halo would shrink. Its outer stars would escape. Its gas could be stripped or compressed. The central region might survive for a while as a dense remnant, continuing to orbit, continuing to lose material, until eventually even that core dissolved or merged so deeply that it could no longer be recognized. This may have taken a long time, many hundreds of millions of years or more. The galaxy did not vanish like a candle being blown out. It unraveled like cloth caught in machinery, thread by thread, loop by loop, until the original pattern was gone. That slow unravelling means the galaxy probably changed appearance many times during its fall. At first, it may have been a self-contained dwarf, then a distorted dwarf with tidal tails, then a remnant core surrounded by streams, then a debris cloud wrapping through the halo. Then, after billions of years, a population of stars spread across the Milky Way's inner halo, no longer obvious in physical space but still linked in motion and chemistry. If we ask what it looked like before it was torn apart, we must remember that there was not just one appearance. There was a life story, a young system, a mature dwarf galaxy, a disturbed satellite, a shredded stream, a dissolved remnant. Its stars would have looked much like stars in other galaxies, because stars are stars wherever they form. Some were probably old red giants by the time of the merger. Some may have been main sequence stars, quietly burning hydrogen. Some massive stars, if any were present in recent star-forming regions before the merger, would have lived short lives and exploded long ago. The stars we see today from Gaia Sausage and Enceladus are the long-lived survivors. Massive bright blue stars from that ancient time would be gone. What remains now are stars with lifetimes long enough to cross billions of years, carrying their chemical fingerprints into the present. This also means that the lost galaxy we reconstruct from surviving stars is biased toward the stars that live a long time. We are reading the durable pages. Short-lived stars have already ended their lives. Gas clouds are gone. Many structural details are erased. That is why astronomers combine present-day observations with simulations. They run models of dwarf galaxies falling into Milky Way-like galaxies, then compare the results with the motions and chemistry we observe. If a simulation produces debris with orbits like the Gaia Sausage stars, and if the inferred mass and timing fit the data, it becomes a possible reconstruction. Not a perfect replay, but a tested scenario. The lost galaxy may also have contained a central star cluster or dense nucleus. Some researchers have considered whether Omega Centauri, one of the largest and most unusual globular clusters in the Milky Way, could be linked to the Gaia Sausage Enceladus progenitor or to another accreted system. Omega Centauri has long been suspected of being the stripped nucleus of a dwarf galaxy, because it contains multiple stellar populations and a spread in metallicity. The connection is still debated and not something to state too strongly, but it shows the kind of clues astronomers look for. A dense cluster with unusual chemistry can be a surviving core of something much larger. Sometimes the heart of a lost galaxy may outlive the body. Whether or not any specific cluster was its nucleus, Gaia Sausage Enceladus likely had enough internal structure to make its destruction complicated. A very small star cluster can be torn into a fairly simple stream. A more massive dwarf galaxy has a broader range of stars, energies, metallicities, and orbits. When it is disrupted, its debris spreads widely. Some stars are stripped early from the outskirts, others are stripped later from deeper inside. This means different parts of the present-day debris may correspond to different parts of the original galaxy. Lower metallicity stars found farther out today may have come from the outskirts of the progenitor, while more enriched stars may have formed closer to its centre. The original galaxy's internal map has been crumpled, but not necessarily burned. There is a plain, almost household way to think about it. Imagine dropping a layered cake into a river. First, let us pause and agree that this is a waste of cake, and probably a poor decision. But imagine it anyway. The outer frosting washes off first, the crumbs break apart, the layers separate at different rates. Downstream, you would not see the cake anymore. You would see bits of it spread out in the water. But if you sampled enough crumbs, frosting and filling, you might begin to reconstruct what kind of cake it was. Chocolate here, fruit there, cream somewhere else. The Gaia Sausage Enceladus galaxy is not a cake, but the method has a similar spirit. The original form is gone. The ingredients remain. Before it was torn apart, the lost galaxy had its own sky. This is a detail we can never observe directly, but it is useful for imagination. If there were planets there, and if some impossible observer had stood on one, the Milky Way might have appeared as a growing presence in the night over cosmic time. At first, perhaps a distant bright galaxy, then larger, then distorted by perspective and motion. As the dwarf fell in, the Milky Way would dominate the sky. Tidal forces would slowly change the home galaxy's shape. Stars would be stripped. The local night would fill with unfamiliar structure. Again, this is not something we know happened from any planet's view, and we should not pretend otherwise. But it helps the scale become personal. To the stars of that dwarf galaxy, the Milky Way was once the outside world. Then it became the whole world. The lost galaxy's shape before the merger probably was not a perfect miniature Milky Way. It likely did not have large, elegant spiral arms like ours. Dwarf galaxies often have irregular shapes, especially if they are gas-rich and forming stars, or spheroidal shapes if they are gas-poor and dominated by old stars. Gaia Sausage Enceladus may have had a stellar body that was compact compared with the Milky Way, with a dark matter halo extending beyond it. Its stars may have been arranged in a rounded or somewhat flattened distribution. If it had rotation, that rotation was eventually overwhelmed by the radial plunge into the Milky Way. The exact morphology is uncertain, so the honest answer is not a single picture but a range. A fairly massive dwarf galaxy, chemically evolved, old, possibly once gas-rich, carrying clusters, and large enough to leave a lasting scar. That uncertainty is not a weakness. It is part of the science. We know the lost galaxy through remains, and remains do not answer every question. They answer enough to give shape to the story, but not enough to remove all mystery. The mass estimates have ranges. The timing has ranges. The amount of gas is uncertain. The original shape is reconstructed rather than seen. This is why careful language matters. It may have looked like this. It likely had that. It probably belonged to this class of dwarf galaxy. Science does not become less beautiful when it admits uncertainty. It becomes more trustworthy, and in a way, more peaceful. The universe is not required to give us a full portrait. We work with the pieces it leaves. What we can say is that Gaia Sausage Enceladus was large enough to matter. It was not just a faint little cluster dissolving at the edge. It was a galaxy whose merger helped build the Milky Way's halo and may have shaken the early disk. Its stars now move through our galaxy on elongated orbits. Its chemistry points to a real, separate history of star formation. Its debris may include globular clusters. Its impact happened so long ago that the Sun formed later inside a Milky Way, already changed by it. So before it was torn apart, it was a meaningful cosmic place, a smaller galaxy with enough substance to become one of the main ingredients in our galaxy's early growth. There is something quietly grounding about that. We often think of the Milky Way as the starting point, the great home galaxy from which our cosmic address begins. But part of its structure came from a galaxy that had its own beginning somewhere else. The lost galaxy formed stars, evolved, fell inward, dissolved, and became part of the Milky Way long before Earth existed. It is gone, and yet its material is still present. Its identity was broken, but its contribution remains. This is not so different from many natural histories. Rivers carry old mountains, grain by grain. Soil contains forests that fell long ago. Our own bodies contain atoms made in ancient stars. The Milky Way contains a galaxy that used to be separate. As we imagine Gaia Sausage Enceladus before its destruction, we should not picture a monster or a victim in any dramatic human sense. It was a galaxy following gravity. The Milky Way was also following gravity. Their meeting was not planned, not cruel, not heroic. It was simply how structure grows in the universe. A smaller system entered the influence of a larger one. The larger one pulled it apart. The pieces became part of something new. And now, billions of years later, we give that lost system a name, study its remains, and try to understand what it looked like before the tearing began. The Milky Way we live in is not simply the galaxy that survived the Gaia Sausage Enceladus merger. It is, in part, the galaxy that came out of it. That difference matters. If the lost galaxy had only sprinkled a few stars into the outskirts and vanished without changing anything else, it would still be interesting, but it would be more like a footnote in the Milky Way's old diary. Instead, the merger seems to have been one of the major events that helped shape the structure we now call home. It added stars, it stirred the halo, it may have heated the early disk, it may have helped trigger new star formation. It changed the way astronomers understand the Milky Way's childhood. The galaxy above us is not only a spiral of stars, it is a spiral that remembers being struck. To see how that works, we have to imagine the Milky Way before the merger, which is not easy because the early Milky Way was not just a smaller version of today's galaxy. We often picture our galaxy as a wide disk with spiral arms, a central bar, a bright bulge, a thin disk, a thicker older disk, and a faint halo around it. But billions of years ago, this structure was still developing. The Milky Way was young, still gathering gas, still forming stars rapidly, still assembling its shape. It had not yet become the more settled system that would later form the Sun. Then Gaia Sausage Enceladus came in, not as a soft drizzle of material, but as a major intruder for the galaxy of that time. A merger that might seem modest compared with the present-day Milky Way could have been very significant when the Milky Way itself was smaller and less settled. The first clear way the merger shaped our galaxy was by helping build the stellar halo. The halo is that wide, faint region around the disk containing old stars, globular clusters, streams, and dark matter. It is not where most of the Milky Way's light comes from, but it is one of the best places to read the galaxy's history. When Gaia Sausage Enceladus was torn apart, many of its stars were scattered into this halo, especially the inner halo. These stars did not settle into the calm rotation of the disk. They moved on stretched, plunging orbits, diving inward and outward through the galaxy. That is why the halo now contains a large population of stars whose motions look as if they came from the same ancient disruption. The merger did not merely add decoration to the outskirts. It supplied a major piece of the halo's old stellar population. This changes the way we think about the halo itself. Without Gaia, it might be tempting to picture the halo as a simple old background population, a faint spherical cloud that formed early and quietly around the disk. But Gaia revealed that the halo is more like a mixed archive. Some stars may have formed in the Milky Way's own early environment, others arrived from smaller galaxies. Gaia Sausage Enceladus appears to be one of the most important of those arrivals. Its stars now move through the halo like old records pulled from another library and placed on our shelves. They are part of the Milky Way now, but their motions and chemistry still show that they were not born in the same original system. The second important effect was dynamical heating. That sounds technical, but the idea is simple enough. A calm disk of stars is dynamically cold, meaning its stars move in fairly organised, nearly circular orbits around the galactic centre. A heated disk is more stirred. Its stars have more random motion. They travel farther above and below the galactic plane. Their orbits are less neatly confined. When Gaia Sausage Enceladus plunged into the young Milky Way, its gravity disturbed the early disk. It did not have to crash star into star. It only had to tug. Over huge scales, gravity is more than enough. The infalling galaxy pulled on the disk, shook it, and altered the orbits of stars that were already there. The result may have helped create or strengthen what we now call the thick disk. Today, the Milky Way has a thin disk and a thick disk. The thin disk is where much of the younger star formation, gas, dust, and spiral structure live. The Sun belongs to the thin disk. The thick disk is older, puffier, and made of stars that travel farther above and below the galactic plane. Its stars are generally older than the thin disk stars and have different chemical patterns. The Gaia Sausage Enceladus merger is not the only possible ingredient in the thick disk's history, but it is widely discussed as a major event that could have heated an early disk and contributed to the thick disk we observe. In other words, some of the Milky Way's thickness may be a scar from an ancient encounter. A helpful way to picture this is to imagine a flat tray of sand. If the tray sits undisturbed, the sand stays in a thin layer. Now tap the tray hard enough, or drop something into it, and grains jump, scatter, and settle into a thicker, rougher arrangement. A galaxy is not a tray of sand, and stars are not grains bumping against each other like particles in a box, but the analogy gives the basic feeling. The early disk had organised motion. The merger shook it gravitationally. Some stars were pushed onto orbits that took them farther from the plane. The disk became puffier. Later, gas could settle again and form a thinner disk, creating the layered structure we see today. It is as if the Milky Way first had an early disturbed layer, then later grew a calmer layer inside and around it. This idea also makes the Milky Way's present calm feel more earned. The galaxy was not born quiet. It passed through a disturbed stage and then it settled. Over time, gas continued to fall in and cool. New stars formed in more organised patterns. The thin disk grew. Spiral structure developed. The Sun formed much later, in a galaxy that had already lived through this major event. So the region we occupy is part of the later, calmer story. But beneath it, in the older stars, is evidence of an earlier, rougher phase. It is a bit like living in a city with smooth, modern streets, then discovering that deep below them are the foundations of older roads twisted by an earthquake. The city functions now, but its structure carries memory. The merger may also have influenced star formation. When a gas-rich galaxy falls into a larger one, the encounter can compress gas, disturb gas flows, and trigger bursts of star formation. Gas behaves differently from stars because gas clouds can collide, lose energy, cool, heat, and collapse. Stars mostly pass through space on gravitational paths, but gas can pile up and respond more directly. If Gaia Sausage Enceladus brought gas into the young Milky Way, or if its passage pushed Milky Way gas inward, it could have helped fuel a period of intense star formation. Some modern studies explore this possibility, suggesting that the merger may have contributed to the formation of metal-rich, thick disk stars through a gas-rich event. That makes the merger not only a story of destruction, but also one of creation. This is one of the strange balances of galaxy evolution. A collision can tear one galaxy apart and help another galaxy form new stars. The same event can be destructive for the smaller system and productive for the larger one. Gaia Sausage Enceladus lost its identity, but its gas and gravitational disturbance may have helped the Milky Way build part of its stellar population. The Milky Way did not simply eat and grow heavier. It responded, it rearranged, it formed. It settled. The merger became part of its internal development, not just an external addition. The merger also likely affected the distribution of dark matter around the Milky Way. This part is harder to see directly, because dark matter does not shine, absorb light, or announce itself with a convenient glow. But the lost galaxy would have had its own dark matter halo, and when it merged with the Milky Way, that dark matter was stripped and mixed into the larger halo. The visible stars are the easiest debris to track, but they were only a small part of the total mass involved. Behind the stars was an invisible gravitational structure. When the merger happened, the Milky Way's dark matter halo also grew and changed. We cannot point to a dark matter stream with our eyes, but simulations tell us that the invisible side of the merger matters. This has consequences for how we understand the Milky Way's mass. Halo stars, especially those on long eccentric orbits, help astronomers probe the galaxy's gravitational field. Their paths respond to the mass distribution of the Milky Way, including dark matter. So the Gaia Sausage Enceladus debris is not only evidence of the past, it is also a tool for measuring the present. The stars from the lost galaxy travel through the Milky Way's gravitational landscape, and by following them, astronomers can learn about the shape and strength of that landscape. A swallowed galaxy becomes a set of test particles, which is a very calm scientific way of saying that the Milky Way accidentally gave us instruments made of ancient stars. There may also be a connection to the Milky Way's central structures, though here we should be careful. Some research has explored whether the Gaia Sausage Enceladus merger could have helped influence the formation of the Milky Way's bar, the elongated structure of stars across the central region of the galaxy. A merger can create tidal forces, drive gas inward, and alter disk dynamics, all of which could make bar formation easier in some simulations. But this is not as settled as the halo contribution or the general heating of the early disk. It is an active question, not a bedtime certainty. So we can say the merger may have affected the inner galaxy in complex ways, but we should not pretend every feature of the Milky Way comes from one event. Galaxies are not that tidy. They are built by many processes at once, which is inconvenient for simple storytelling but much better for reality. Another way the merger shaped the Milky Way was by bringing in globular clusters. Some clusters now orbiting the Milky Way may have belonged to Gaia Sausage Enceladus before the merger. Globular clusters are dense, old star systems, and because they are tightly bound, they can survive the destruction of their parent galaxy. If a dwarf galaxy is torn apart, its loose stars spread into the halo, but some of its clusters can remain intact for billions of years. That means part of the Milky Way's globular cluster system may have been imported. The clusters are like sealed relics, still holding together after the larger system that carried them in was destroyed. They add to the sense that the Milky Way is a collection, not a single origin object. This collected nature is important. The Milky Way is often introduced as one galaxy, and of course it is one galaxy now. But it is also the result of many earlier parts. Some stars formed in place, some formed in gas that settled into the disk, some came from accreted dwarf galaxies, some clusters may have been captured, some streams are still being pulled apart today. Gaia, Sausage and Enceladus was not the only merger, but it was one of the most important early ones. It helped show that the Milky Way's family history is not a simple line. It is a merger tree, with branches that join, disappear, and become part of the trunk. The idea of a merger tree is useful because it places the Milky Way in a wider cosmic pattern. In modern cosmology, large galaxies grow through hierarchical assembly. Small systems form first, then merge into larger systems over time. The Milky Way did not appear fully formed. It grew by gathering gas, forming stars, and accreting smaller galaxies. Gaia Sausage Enceladus is one of the clearest local examples of that process. It is the cosmic web's construction method written into our own galaxy. The same principle that builds galaxy clusters and large-scale structure also shaped the quiet band of light visible from Earth. Home, in this sense, is a product of cosmic assembly. What makes Gaia Sausage Enceladus especially important is that it happened early enough to influence what came after. If a small galaxy falls into the Milky Way today, it adds debris to an already mature system. The Sagittarius dwarf is doing something like that now, but Gaia Sausage Enceladus fell in when the Milky Way was still young, so the effect was deeper. It helped define the early halo. It disturbed the early disk. It may have helped set up later phases of disk formation. The present Milky Way carries that early adjustment in its architecture. It is like a tree bent by weather when it was young. Even after it grows larger and stronger, the shape of the trunk still remembers the storm. There is also a timing connection with the Milky Way's two-phase formation history. Gaia-based studies suggest that parts of the thick disk are very old, and that the formation history of the Milky Way may have gone through distinct phases, with early thick disk formation followed by the major Gaia Sausage Enceladus merger, and then later growth of the thin disk. In this picture, the merger was not the beginning of everything, but it was a major turning point. It helped close one stage and shape the next. The early Milky Way was already forming stars, then the merger accelerated changes in the halo and disk, and later the galaxy continued building the calmer thin disk where stars like the Sun would eventually form. That sequence makes our own position in the story feel slightly different. The Sun did not form in the middle of the merger. It arrived much later, after the Milky Way had already absorbed the lost galaxy and settled into a new phase. The solar system formed from gas enriched by earlier generations of stars, inside a disk shaped by events that had long since faded from direct view. The Gaia Sausage Enceladus merger did not make Earth in any simple direct way, but it belongs to the background history of the galaxy that made Earth possible. It helped shape the environment in which later star formation continued. It is part of the long chain of conditions that led to the Milky Way we inhabit. This is one reason the merger feels both remote and personal. Remote, because it happened billions of years before us. Personal, because it shaped the galaxy we call home. We're used to thinking of our home as Earth, perhaps the solar system if we're feeling expansive, and the Milky Way if we're in a particularly cosmic mood. But the Milky Way itself is an inherited structure. It was changed by a galaxy that no longer exists. So when we say we live in the Milky Way, we're also living in the aftermath of Gaia Sausage Enceladus. Not dramatically, not in a way that changes your breakfast or your plans for tomorrow, but physically, historically, structurally. The old collision is built into the galaxy around us. There is a gentle irony here. The lost galaxy is gone, yet it helped make something lasting. Its stars continue moving through the halo, its possible clusters still orbit. Its dark matter contributed to the larger halo. Its impact stirred and shaped the early disk. It was destroyed as an independent galaxy, but it did not become meaningless. In cosmic history, being absorbed does not always mean being erased. Sometimes it means becoming part of a larger structure so thoroughly that the larger structure cannot be understood without you. The Milky Way we see today is therefore not a quiet spiral that somehow escaped the roughness of the universe. It is a quiet-looking spiral that has already endured roughness. Its beauty is not separate from its past. The thin disk, thick disk, halo, bulge, bar, streams, clusters, and satellite galaxies all belong to a system still carrying the results of gravity's long work. The Gaia Sausage Enceladus merger is one of the major old events that tells us this. It says that the Milky Way was hit, stirred, fed, and enlarged. It says that some of the stars around us are not native to the galaxy's first structures. It says that even a galaxy that feels like home can be partly made from elsewhere. And now, as we follow that idea outward, the next question becomes where those remains are today. By the time a galaxy has been torn apart for billions of years, its remains do not always look like remains. They do not sit in a tidy pile. They do not glow with a label beside them. They are not arranged like wreckage after a shipwreck with broken boards floating together in one patch of sea. The debris of Gaia Sausage Enceladus is stranger than that, and much more spread out. Some of it is in stars moving through the Milky Way's halo. Some may be in globular clusters that once belonged to the lost galaxy and survived the tearing. Some is probably in dark matter we cannot see directly. And some of it is mixed so deeply into the Milky Way that it is less like finding pieces of an old object, and more like realizing that the old object has become part of the walls, the floor, and the air of the house. This is why the word ghost fits the story so well, as long as we use it gently. A galactic ghost is not supernatural. It is not a pale figure drifting between constellations, though that would certainly make telescope proposals more dramatic. A galactic ghost is a remnant of something that used to be separate and is now only partly recognizable. The original galaxy is gone, but its presence lingers in motion, chemistry, structure, and gravity. It has no clear body anymore. It cannot be photographed as a little galaxy beside the Milky Way, yet it still affects the way we understand the stars around us. It is gone in one sense and present in another, which is exactly the kind of thing ghosts are supposed to do in stories, except this one is made of stellar orbits rather than candlelight and creaking floorboards. The most direct remains are the stars themselves. The Gaia Sausage stars are scattered through the Milky Way's halo, especially the inner halo, moving on those long, stretched radial orbits we have been following. They plunge inward toward the galaxy's centre and then swing outward again, carrying the old memory of the smaller galaxy's fall. These stars are not grouped into one bright patch, because time has had billions of years to spread them around. Their original home has been stirred into the Milky Way, but if you measure their motions carefully, they still behave like relatives. Not identical, not perfectly aligned, but related. They share a dynamical fingerprint, a way of moving that points back to a common origin. The halo is the natural hiding place for such ghosts. It surrounds the Milky Way's disk in a huge, faint region that is difficult to notice without careful surveys. The disk is bright and full of stars, gas, dust, and the spiral structure that gives the galaxy much of its visible character. The halo is quieter. It is older. It is thinly populated by comparison, but it contains some of the best evidence of the Milky Way's past mergers. A disk can settle and form new stars after a disturbance. A halo can preserve the debris of older events for a very long time. If the Milky Way's disk is the active face of the galaxy, the halo is the old storage room where the records are kept. Though it is a storage room tens of thousands of light years wide and very inconvenient to dust. Some remains are easier to picture as streams. Stellar streams are long trails of stars pulled out of globular clusters or dwarf galaxies by the Milky Way's gravity. When a smaller system orbits the Milky Way, tidal forces can strip stars from it. Those stars do not simply fall randomly into the galaxy. They stretch ahead of and behind their parent system along its orbit, making long ribbons across the halo. In telescope images and star maps, some streams look like faint threads. Others are so thin and subtle that they only appear when astronomers use careful filtering, motion measurements, and statistical methods. They are some of the most beautiful forms of galactic debris, not because they are bright to the eye, but because they show gravity drawing a path through time. The Gaia Sausage debris itself is not usually described as one simple narrow stream today, because it is older and more thoroughly mixed than many younger streams. That is an important distinction. A recent disruption can leave a clean ribbon, like a fresh scratch across the halo. An ancient major merger leaves a broader, more blended population, with stars wrapped around the galaxy over many orbits. So when we talk about stellar streams in this part of the story, we are looking at the wider family of galactic remains around the Milky Way, and at the way these streams help us understand what happens when systems are pulled apart. Gaia Sausage Enceladus is one of the older, larger ghosts. Other streams are younger and sharper, showing the same kind of process at different stages. The Sagittarius stream is a good example of a more current disruption. The Sagittarius dwarf spheroidal galaxy is being torn apart by the Milky Way right now, in cosmic terms, leaving trails of stars wrapped around our galaxy. It gives astronomers a living demonstration of what tidal stripping looks like while the parent galaxy is still partly recognizable. The Gaia Sausage is the old version of that kind of story, after the parent galaxy is dissolved beyond ordinary recognition. If Sagittarius is a half-unravelled sweater still hanging from the chair, Gaia Sausage Enceladus is the wool already knitted into another blanket. You can still trace some threads if you know what to look for, but the original garment is no longer there. Other stellar streams come from globular clusters. These clusters are dense balls of old stars orbiting the Milky Way, and as they move through the galaxy's gravitational field, they can lose stars from their edges. Those escaped stars form thin streams, sometimes stretching far across the sky. The stream does not always shout its presence. It may contain faint stars spread so sparsely that only a precise survey can reveal them. Gaia has been especially useful here because streams are not only about where stars are, but how they move. A group of stars sharing a path through space can stand out even when it's hard to see as a simple line. Motion becomes the thread that ties them together. These streams are valuable because they are sensitive to gravity. A stellar stream follows an orbit shaped by the Milky Way's mass. If the stream is bent, widened, disturbed, or broken in a certain way, astronomers can ask what gravitational influence caused that. Was it the smooth pull of the Milky Way's dark matter halo? Was it a close encounter with a giant molecular cloud? Was it the passage of a dark matter subhalo, a small clump of dark matter with little or no visible stars? Streams are like measuring tapes laid across the halo, except the measuring tape is made of stars, and the thing being measured is an invisible gravitational field. A perfectly normal project, really, if your office happens to be a galaxy. Dark matter makes the remains story much deeper. The visible stars from Gaia Sausage Enceladus are only the part we can easily track. The original dwarf galaxy almost certainly had a dark matter halo around it, because dwarf galaxies are usually dominated by dark matter. When it fell into the Milky Way, that dark matter halo would have been stripped first, spread out, and mixed into the Milky Way's own dark matter halo. We cannot see this debris directly. It does not glow. It does not make a stream of light. It does not show up as a beautiful ribbon on a sky map. But gravitationally it should be there, part of the invisible mass structure around the Milky Way. This means the Milky Way did not only inherit stars from the lost galaxy, it inherited invisible matter as well. In fact, if the original galaxy's dark matter halo was much more massive than its stars, then most of what fell in was invisible. That is one of the strangest parts of galaxy formation. The bright debris gets the photographs and the names. The dark debris does much of the gravitational work. The stars let us trace the event, but the dark matter helped carry the mass. When astronomers simulate a merger like Gaia Sausage Enceladus, they include not only stars but dark matter halos, because without them, the merger would not behave correctly. The ghost has a visible outline, but most of its body is unseen. This matters for the Milky Way today because the dark matter halo affects how stars move, how streams bend, and how satellite galaxies orbit. If Gaia Sausage Enceladus contributed a large amount of dark matter, then part of the Milky Way's present invisible halo may be merger debris from that ancient event. It is difficult to separate one dark matter contribution from another, because dark matter does not carry chemical fingerprints the way stars do. Stars can reveal their birth environments through spectra. Dark matter, at least as we currently understand it, gives us only gravity. It is like trying to reconstruct a meal when one of the main ingredients has no taste, no smell, and no colour, but still somehow determines whether the table collapses. The globular clusters connected to Gaia Sausage Enceladus are another kind of remnant. Some studies identify sets of Milky Way globular clusters whose orbits and properties suggest they may have come in with this merger. These clusters are old, dense, and tough enough to survive when their parent galaxy was destroyed. That gives them a special status. A loose star is one clue. A globular cluster is a preserved community. It may contain hundreds of thousands of stars that stayed gravitationally bound while the larger galaxy around them unraveled. If some clusters came from the lost galaxy, then they are surviving islands from an absorbed system, now orbiting inside the galaxy that consumed their old home. Their survival also helps astronomers estimate the original galaxy's importance. A dwarf galaxy massive enough to host several globular clusters is not a trivial object. It had enough mass and history to build or carry these dense old systems. Comparing the ages, metallicities, and orbits of globular clusters can help researchers sort which ones likely formed in the Milky Way and which ones were accreted from smaller galaxies. This is not always easy. Globular cluster family trees can be messy. But when clusters share the right orbital characteristics and chemical patterns, they can point back to a common accretion event. The Milky Way's cluster system becomes a museum where some exhibits were made locally and others arrive from vanished galaxies. There are also possible remnants in the form of individual very old stars near the Sun. Some halo stars pass through our neighbourhood on plunging orbits, making them accessible for detailed study. These stars may be part of the Gaia Sausage Enceladus debris. They are not close in the everyday sense, but close enough for surveys to measure their motions and chemistry carefully. That makes the lost galaxy feel less remote. Its remnants are not only in the farthest halo. Some of its stars travel through the broader region around us, mixed into the sky above our little patch of the disk. A star that began in another galaxy may pass through the Milky Way near the Sun, quietly crossing our cosmic neighbourhood without looking unusual to the naked eye. This is one of the reasons Gaia transformed the subject. Before precise motion data, many accreted stars would have blended into the general background. A star can look ordinary while having an extraordinary orbit. Gaia gave astronomers the ability to connect motion across huge numbers of stars. Once you know how a star moves, it stops being just a point of light and becomes part of a dynamical story. A halo star plunging in and out through the Milky Way is a different kind of clue from a disk star moving with the rotation. The old ghosts were not hiding because they were invisible. They were hiding because we had not measured the right thing well enough. The phrase "around us" should also be understood in a galactic way. The remains are around us not like furniture in a room, not like trees around a house, but spread through the large structure of the Milky Way. We are inside the disk and the halo surrounds the disk. The Gaia Sausage debris moves through that halo and inner galaxy, so in a broad cosmic sense, we live within a galaxy filled with these remains. Some are above the disk, some below, some plunging through inner regions, some on orbits that carry them outward. They are not evenly distributed like mist. They are part of a complex orbital population. But they are part of our galaxy now, and our galaxy surrounds us. There is something quietly strange about knowing that the Milky Way's halo contains debris from multiple events. Gaia Sausage Enceladus is a major one, but not the only one. There are other named structures, other streams, other accreted populations, other possible merger remnants still being studied. The halo is less like a single ancient shell and more like a layered field of leftovers. Some debris is from galaxies, some is from clusters, some is old and blended, some is young and sharp, some may not be fully understood yet. Every new survey improves the map, and every improved map complicates the story in useful ways. The Milky Way is not one ghost story. It is a whole haunted archive, though a very quiet one. These ghosts also help us understand the future. The Milky Way is still surrounded by smaller companions. The Sagittarius dwarf is being disrupted. The Magellanic clouds are interacting with the Milky Way and may eventually merge. Far in the future, Andromeda will meet us in an enormous merger that will reshape both galaxies. The remains around us are not only evidence of what happened long ago, they are examples of what galaxy growth continues to do. The Milky Way is not finished. Today's satellite can become tomorrow's stream. Today's stream can become the next generation's blended halo population. A sharp remnant becomes a diffuse ghost, and a diffuse ghost becomes part of the galaxy's background. The dark matter side of this future is just as important as the stars. As smaller galaxies fall in, their dark matter halos are stripped and added to the Milky Way's halo. This process builds the invisible structure around the galaxy over time. The visible stellar streams are helpful because they respond to that invisible mass. If dark matter is clumpy on small scales, as many models suggest, then streams may show gaps, wiggles, or density variations from encounters with dark subhalos. That is one reason astronomers care so much about mapping streams. They are not just pretty leftovers, they may be one of the best ways to test what dark matter is doing at scales where we cannot see it directly. The remains of Gaia Sausage Enceladus, then, are part of a larger toolkit. The radial halo stars tell us about a major early merger. The possible globular clusters tell us about the lost galaxy's mass and companions. The streams around the Milky Way show ongoing and past disruption. Dark matter debris reminds us that most of the merger's mass may be invisible. Together they reveal a galaxy built through capture, tearing, mixing, and settling. The Milky Way is not a clean spiral floating untouched in space. It is a structure with seams. Some seams are visible only in motion, some only in chemistry, some only in gravity. A nice way to hold this in mind is to picture the night sky as less of a flat view, and more of a map with hidden layers. The first layer is what your eyes see, the bright stars, the Milky Way band if the sky's dark enough, the familiar constellations. The second layer is distance, because some stars are nearby and others are far away. The third layer is motion, because each star is travelling through the galaxy. The fourth layer is chemistry, because each star formed from gas with its own history. The fifth layer is dark matter, invisible but shaping the paths of everything. Gaia Sausage Enceladus appears when those deeper layers are studied together. It is not obvious at the surface, it is a structure in the hidden layers. That is why the word ghost is useful again. A ghost is something you do not see directly at first. You notice a door moving, a floorboard creaking, a cold patch in the room. In astronomy, the clues are more respectable and less likely to upset the furniture. A group of stars has unusual motion. A set of clusters shares orbital properties. A halo population has a chemical pattern. A stream bends in a way that suggests hidden mass. None of these is the lost galaxy in full. But together, they point to something that was there. A system that lived, fell in, broke apart, and became part of the Milky Way. And perhaps the most restful thought in all of this is that these remains are not rushing anywhere on our timescale. They are moving quickly in physical terms, yes, but their story unfolds slowly. The stars continue their long orbits. The streams continue wrapping through the halo. The clusters continue circling. The dark matter continues shaping the gravitational field. While we sit here for a few quiet minutes, trying to let the day settle, These ancient remnants are still doing what they have done for billions of years. They move through the galaxy. They preserve the past. They wait for measurement. So when we say the Milky Way ate a galaxy, and it is still around us, this is what we mean. We mean the meal was never fully erased. It became halo stars on strange orbits. It became possible globular clusters. It became invisible dark matter debris. It became part of the galaxy's old structure. It became clues scattered across the sky, not obvious to the eye, but clear enough to instruments like Gaia, and to the astronomers patient enough to read the motions. The lost galaxy is not beside us anymore. It is around us through the Milky Way, inside the history of the halo, present in the same great star system that carries the sun. What the Gaia Sausage reveals more than anything is that the Milky Way has never been a perfectly quiet place. It may look quiet from Earth, especially when it appears as that pale band across a dark sky, but its history is not a simple story of gentle rotation and steady starlight. It is a history of growth. It is a history of gravity pulling smaller systems inward, of stars being scattered into new paths, of gas being stirred, of old disks being heated, of halos being built from things that used to be separate. The Milky Way is beautiful, yes, but it is not untouched. It is calm in the way an old landscape can be calm after storms have shaped every hill, valley and riverbed. The surface rests. The history remains. Before Gaia helped reveal this ancient merger, it was easier to imagine the Milky Way as a single, continuous structure, a galaxy that formed, settled, spun, and eventually became the home of the sun. That picture was never completely wrong, but it was incomplete. Gaia Sausage and Enceladus showed that a major part of the Milky Way's early story came from outside. A smaller galaxy fell in, was torn apart and left behind a large population of stars in the halo. Those stars do not move like ordinary disk stars. They plunge inward and outward on stretched orbits, as if still remembering the direction from which their old galaxy arrived. Their chemistry, motion and age tell us they were not simply born as part of the Milky Way's calm rotating disk. They came from another system, and their presence means our galaxy's past is not only internal, it is also inherited. That is a powerful idea, because it turns the Milky Way from a finished object into a living record of assembly. Not living in the biological sense, of course. The Milky Way is not breathing quietly in the dark, although after spending enough time with astronomy, one can almost forgive the imagination for trying. It is living in the structural sense. It has changed. It has grown. It has absorbed material. It has been reshaped by encounters. It has a history written into its stars. The Gaia Sausage is one of the clearest reminders that galaxies are not born once and then left alone. They are built over time, and sometimes the building process involves one galaxy losing its separate identity so another can become larger and more complex. The violent part of this history is not violence in the way we usually picture it. There were no stars smashing together like sparks from a grinder. The distances between stars are too large for that to be common. The violence was gravitational. It happened in orbits, tides, and distortions. The smaller galaxy was pulled apart because the Milky Way's gravity tugged more strongly on one side than the other. Its dark matter halo was stripped. Its stars were loosened. Its gas, if it still carried much gas, was disturbed or lost. Its clusters were either scattered or left to orbit as dense survivors. Over time, the original system dissolved. The destruction was slow, but it was still destruction. A galaxy that once had its own centre, shape and history became debris inside a larger galaxy. Yet the same event also helped create the Milky Way we now study. That is the strange double nature of mergers. They destroy and build at the same time. Gaia Sausage and Enceladus was destroyed as an independent galaxy, but the Milky Way gained stars, dark matter, and perhaps gas. The early disk may have been stirred and thickened. The inner halo gained a major population of accreted stars. The galaxy's future path changed. So when we look at the Milky Way today, with its thin disk, thick disk, halo, central regions, streams and clusters, we are not seeing a clean structure made by one process. We are seeing the result of many processes layered together: quiet star formation, gas settling, supernova enrichment, dark matter gravity, satellite disruption, major mergers, minor mergers, long periods of settling. A galaxy is less like a single statue and more like an old city, rebuilt many times, with older stones still visible if you know which alley to look down. The Gaia Sausage also reveals that the halo of the Milky Way is not just a faint outer decoration. It is one of the main archives of our galaxy's past. The disk is bright and familiar because it contains so many stars and gas clouds, but the halo preserves ancient debris in ways the disk often does not. Stars in the disk tend to share the rotation of the galaxy. Halo stars can move on stranger paths, and those paths can preserve the memory of accretion events. This is why Gaia was so important. It allowed astronomers to read the halo not simply as a dim cloud of old stars, but as a set of moving populations. The halo became a fossil record, not made of stone, but of velocity. That may be one of the most important lessons of the entire story. A fossil does not have to sit still. The stars of Gaia Sausage and Enceladus are moving quickly through space. They are crossing the Milky Way on enormous orbits. They are not frozen relics in a museum case, but their motion is the fossil. Their paths are the preserved evidence. It is a different kind of remembering, and a very useful one. On Earth, we learn about ancient animals from bones, footprints, and impressions in rock. In the galaxy, astronomers learn about ancient mergers from orbits, chemical fingerprints, and the distribution of stars. The Milky Way is full of moving fossils, and Gaia gave us the ability to recognize some of them. This changes the way we think about the stars around us. A star is not just a light. It is a place with a history. It formed from a particular cloud of gas. That gas had a chemical composition shaped by earlier stars. The star began with a particular motion, inherited from the system where it was born. Over time, gravity carried it through the galaxy, or perhaps into another galaxy altogether. So when a halo star from Gaia Sausage Enceladus passes through the Milky Way today, it is carrying several kinds of information at once. Its chemistry tells us about the lost galaxy's star formation. Its orbit tells us about the merger. Its age tells us how early that system formed. Its present position tells us how thoroughly the debris has been mixed. A tiny point of light becomes a witness, if we are patient enough to question it properly. The merger also reveals that our galaxy's calm present is not separate from its restless past. The Sun formed long after Gaia Sausage and Enceladus fell in. Earth formed in a Milky Way that had already been changed by that ancient event. The old collision did not happen to us directly, but it happened to the galaxy that eventually made room for us. That is a subtle kind of connection. We cannot say that the Gaia Sausage made Earth, not in any simple way. But we can say that it helped shape the galactic environment that existed before the Sun was born. It is part of the background history of our cosmic address. Before Earth had oceans, before the Moon raised tides, before the first life appeared, the Milky Way had already swallowed another galaxy and settled into the aftermath. There is something humbling about that timeline. The merger was already ancient when our solar system began. The stars from the lost galaxy had already been moving through the halo for billions of years before the Sun lit up. By the time humans began drawing constellations, telling stories about the Milky Way, and wondering what that pale band might be, Gaia Sausage and Enceladus had long since vanished as a separate object. Its stars were still there, but no one could yet know what they meant. The evidence was overhead all along, hidden not by distance alone, but by lack of precision. It took a spacecraft measuring tiny motions across the sky to reveal that some of the stars around us were carrying a story older than Earth. This is one of the gentle surprises of modern astronomy. Sometimes the biggest discoveries come from measuring small changes very carefully. Gaia did not need to see the ancient collision directly. It could not. No instrument can fly backward through 10 billion years and watch the dwarf galaxy fall in. Instead, Gaia measured where stars are now and how they move now. From that, astronomers reconstructed what likely happened long ago. The present became a doorway into the past. That is an extraordinary thing, and also a very ordinary scientific habit. We look at what remains, we ask what could have produced it. We test the answer with data, simulations, chemistry, and comparison. Slowly, a hidden history becomes visible. The Gaia Sausage also tells us that the Milky Way is not unusual in being messy. This is how galaxies grow. Across the universe, larger galaxies absorb smaller ones. Stellar streams wrap around halos. Dwarf galaxies fall inward. Dark matter halos merge. Gas is stripped, compressed, and stirred. The Milky Way story is local, but the process is cosmic. Our galaxy is one example of a wider pattern known as hierarchical formation, where small structures build larger ones over time. The phrase sounds rather tidy, but the reality is not always tidy. It is a universe of joining, tearing, mixing, and settling. The Gaia Sausage matters because it lets us study that process from inside one galaxy in unusually rich detail. We're not only looking at distant galaxies and guessing, we are reading the merger record of our own home. It also reminds us that names like Milky Way can hide complexity. We give a galaxy one name because it is useful, but inside that one name are many origins. Some stars formed in the early Milky Way. Some formed in gas that later settled into the disk. Some came from Gaia Sausage and Enceladus. Some came from other accreted systems. Some may still be arriving from smaller companions. The Milky Way is a single galaxy now, but it is not made from a single beginning. Its identity is assembled. This may feel strange at first, but it is common in nature. A river is fed by many streams. A forest grows from generations of fallen leaves. A person is made of atoms forged in stars that lived and died long before Earth existed. A galaxy too is a mixture with memory. The violent past of the Milky Way is therefore not something separate from its beauty. It is part of why the beauty exists. The halos, old stars, the thick disks, ancient populations, the possible imported globular clusters, the layered chemical patterns, all of these are pieces of the same history. The Milky Way's gentle band across the sky is not beautiful because nothing ever happened to it. It is beautiful because so much happened, and because after all that motion, disruption, and growth, the galaxy settled into a form that could hold stars like the Sun and planets like Earth. Calm is often not the absence of disturbance. Sometimes calm is what remains after disturbance has had enough time to become structure. The discovery also gives us a clearer sense of scale. A galaxy can absorb another galaxy, scatter its stars across tens of thousands of light years, and still look peaceful to creatures living inside it billions of years later. That is the scale on which the Milky Way lives. It carries disasters so old and so large that they become architecture. It folds a smaller galaxy into itself, and then, much later, a planet forms, life appears, and someone lies awake wondering why the sky looks so still. The answer is that stillness is often an illusion created by time. We live too briefly to see the full motion, so we build instruments that extend our patience. We make maps that show what eyes cannot hold. We let data reveal the slow violence beneath the quiet surface, and the story is not finished. The Milky Way still has companions. The Sagittarius dwarf is being torn apart now, leaving streams around the galaxy. The Magellanic Clouds are interacting with the Milky Way and will continue to shape its future. And far ahead, the Milky Way and Andromeda will merge, creating a galaxy very different from either one today. Gaia Sausage Enceladus is ancient history, but it is also a preview. It shows what happens when galaxies meet, what remains when one is swallowed, and how future astronomers, if any exist in the far future, might read the remnants of our own galaxy's next great transformation. Today's home is tomorrow's fossil record. A comforting thought, perhaps, if you're very relaxed about galactic timescales. For now, though, the Gaia Sausage gives us a rare chance to understand our own galaxy more honestly. It reveals that the Milky Way's halo is full of memory. It reveals that some stars around us were born elsewhere. It reveals that the thick disk and inner halo may owe much of their present character to an ancient merger. It reveals that even a quiet-looking spiral can have a rough youth. And it reveals that the story of home is larger than home itself. The Milky Way is not a sealed island in space. It is a collection of histories, some local, some imported, some still recognizable, some almost erased. So the next time you see the Milky Way, if you're lucky enough to stand beneath a dark enough sky, perhaps it will look a little different. Still soft, still quiet, still stretched across the night like a pale path. But now, hidden inside that calm, there is a deeper awareness. Some of the stars in and around our galaxy came from a lost place. Some move through the halo on paths that began with an ancient plunge. Some are part of a galaxy that the Milky Way absorbed so long ago that only motion can still name it. The sky is not just overhead. It is historical. It is layered. It is full of old arrivals, and here we are, inside that history, very small and very late, listening from one little planet in the disk. The galaxy turns around us with no hurry at all. The halo stars keep their long orbits. The old debris keeps moving. Gaia's measurements continue to help astronomers refine the story one star at a time, and the Milky Way, our great familiar home, becomes both more complicated and more wonderful. Not a perfect, untouched spiral, but a survivor, a collector, a galaxy built from itself and from others. If this quiet journey through the Milky Way's swallowed past has given you a little calm or a little wonder, or simply something interesting to carry with you towards sleep, I'd be ever so grateful if you liked the video and subscribed. It helps this cozy corner of science reach others who might enjoy drifting through the universe at a gentler pace. And if you are still awake, perhaps let the final thought be this. The Milky Way ate a galaxy, and that galaxy is still around us. Not as a separate island of stars, not as a visible shape in the sky, but as motion, memory, and ancient light. We live inside the aftermath. We look up through the evidence, and somewhere in the quiet halo, the stars of a lost galaxy are still moving, patiently carrying the story of how our galaxy became home,